Bueno, probando. Y va a haber preguntas. No hay preguntas. Siguiente, 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 siguiente.
Station in automation, what as well as a bachelor's degree in mechatronics engineering from the Universidad Autónoma de San Luis Potosí. His research focused on the application of the intelligent technologies for the identification and control of dynamic systems, with an emphasis on neural networks, embedded platforms, and real-time automation. He has author per review publication in indexed journals such as EAAA Access, and has presented an international conference including ICECCME and ADCIS. He also holds registered software copyrights related to the automated design of neural network architectures for control systems. He has actively contributed to the curricular design of the WAP's Bachelor of Science in Cybersecurity Engineering, promoting advanced training in automation and digital security. He currently tasks research initiatives, mentors graduate thesis, and for the development of academic talent in robotics, artificial intelligence, and industrial cybersecurity. Please give us a applause and begin, please.
Thank you. Bueno, el día de hoy les vengo a hablar un poco de la parte de ciberseguridad aplicada a la automatización, porque muchas veces nos enfocamos en automatizar, en que todo salga bien, pero nunca en la seguridad, ¿no? Entonces les voy a dar como un rápido panorama de qué es lo que siempre hay que tener en cuenta en este sentido, ¿no? Y que sepan que también hay una, digamos, ciencia que se dedica a esa parte de la seguridad, ¿no? Entonces, como recordarán, como se imaginarán, pues las revoluciones de la industria han ido avanzando. Obviamente, al principio no había nada de tecnología, nada de interconexión, todo era muy mecánico, etcétera. Pero como ustedes sabrán y han observado, en toda esta parte de la automatización y eso, que sobre todo es en lo que más estamos enfocados, pues se ha ido mezclando un poco lo que es la tecnología informática con la tecnología operacional, ¿no? Todo lo que es la información, lo que llamamos la revolución industrial 5.0. Entonces se ha ido transformando o se ha ido digitalizando todo lo que es la industria de la automatización. Cada vez queremos controlar las cosas más desde cualquier lugar, queremos tener la información resumida. Obviamente el dueño de una empresa, ¿qué es lo que quiere? Pues por en cualquier momento poder sacar su celular y revisar cómo va todo lo que es la producción, ¿no? Pero pues eso obviamente lleva sus riesgos, sus partes malas o sus partes difíciles, que es donde hay que trabajar y cuidar, ¿no? Entonces cada vez se va expandiendo más las partes donde puede llegar a ser atacado un sistema, ¿no? ¿Cuáles son las partes que realmente se van vulnerando? Una es que, como ustedes sabrán, hay muchos dispositivos en las empresas que son de legacy, ¿no? Lo que le llaman, que son aparatos que llevan sirviendo en una empresa a lo mejor 20, 30 años. Hay servidores que no se han reiniciado en 20 años. Entonces, esos dispositivos que les llamamos legacy, pues son un peligro porque hay algunos equipos que siguen usando, no sé, Windows XP, Windows 2000, Windows Server. Es algo muy conocido que hay muchos cajeros en el mundo que siguen utilizando Windows XP cuando ya es muy inseguro, ¿no? Entonces, ese tipo de dispositivos legacy son un problema. Además de que exponer el ICS, que es el Industrial Control Systems, a redes, digámoslo así, externas, como lo es el Internet, pues obviamente eso va extendiendo cada vez más el lugar donde se puede llegar a dar un ataque. Utilizar tecnologías estándar como Internet o Ethernet, TCP/IP, tecnologías que no están pensadas para asegurar la información, pues obviamente eso también pone en riesgo, ¿no? Y pues obviamente aumentamos el riesgo de un ataque o de ataques cibernéticos a lo que tenemos, ¿no? Entonces, si se dan cuenta, el problema es que cada vez vamos conectando más cosas a la red que tenemos ya de automatización. Como les decía, los dispositivos anteriores, esta parte de lo que es el SCADA, que el SCADA es el Supervision, Control and Data Acquisition, toda la información de la automatización y donde se hace el control. Entonces, todo eso, al final de cuentas, lo estamos conectando a lo más peligroso que hay, que pues es el Internet, ¿no? Donde hay muchas personas, muchas, sí, digamos que es su trabajo, ¿no? Prácticamente, poder robar toda esta información. Entonces, Ahora, ¿por qué es importante? Pues ustedes dirán, no pasa nada en que me apaguen mi robot, algo que está automatizado. Pero sabemos que ya estos niveles automatizados están prácticamente todo, ¿no? La mayoría de las cosas, como lo son infraestructuras como energía, agua, empresas, transporte, obviamente plantas nucleares, todo lo que es ya, digamos, vital para una sociedad. Y ya se pone en riesgo, ¿no? Entonces, estos ciberataques, estos incidentes, ¿qué pueden causar? Pues problemas físicos o daños físicos a instalaciones, que se detengan líneas de producción, impacto en todo lo que es, por así decirlo, el ecosistema de lo que es la empresa y obviamente lo que no me gusta de las empresas, familias económicas, ¿no? Entonces, por eso es que es importante tomar en cuenta esta parte de la comunidad cuando hacemos automatización. Entonces, ¿qué es lo que nos afecta o cómo entra esta parte global en todo lo que es el desarrollo de la automatización? Pues incrementa las posibilidades de recibir un ciberataque. ¿Y cuáles son generalmente las motivaciones de este tipo de ataques? Uno puede llegar a ser el espionaje industrial. Sabemos que en la actualidad hay muchas empresas que cuidan justamente sus desarrollos tecnológicos, etcétera. Entonces pueden llegar a recibir perdón, ciberataques para poder hacer espionaje. Ya prácticamente cuando vas a ver con una empresa grande van a hacer un producto, ya un mes antes ya está todo filtrado, ¿no? Por ese tipo de cosas. Pero obviamente estos desarrollos tecnológicos llevan más tiempo. Entonces, pues esta parte del espionaje industrial es una de las motivaciones, ¿no? Sabotaje económico, obviamente. Extorsión, hace más o menos unos 6, 7 años, hubo algo muy mundial, por así decirlo, que fue la ransomware, que lo que hacía ese virus era secuestrar datos. Simplemente los encriptaban, tú los podías borrar las claves. Obviamente podías borrar la información y no pasaba nada, pero nosotros, si nos encriptan una información y nos piden dinero para rescatarla, pues podemos no pagar y no pasa nada, no es nuestra información, no pasa nada. Pero hay empresas que tienen ahí guardado muchísima información que no es tan fácil como decir, pues no les pago y se reinicia, ¿no? Entonces, esto fue económicamente muy grande y pues consecuencias ya con problemas físicos e impactos económicos y físicos, como lo vamos a ver ahorita más adelante en algunos ejemplos que hubo. Ahí está. Y les voy a dar unos 2 o 3 casos que hubo. Uno pasó en el 2010, que le llamaron el Stuntex, porque así se le llamó al virus. Y como aquí lo que dice es que es un malware que fue diseñado para sabotear centrifugadoras nucleares. Como sabrán decir resumen, se necesita enriquecer uranio para todo lo que es nuclear, ¿no? Pues resulta que Irán, ahora con lo que ha habido últimamente, este virus justamente atacó a unas centrifugadoras que hubo en Irán y atacó específicamente a unos sistemas Siemens, que pues, como ustedes conocerán y han trabajado con Siemens, pues es de las empresas más grandes de automatización, ¿no? Entonces, ¿qué era lo que hacía este virus? Pues modificaba comandos de PLC sin que fuera detectado. Entonces, el PLC, ¿qué hace? Pues controla todo el sistema de automatización, podemos provocar daños físicos. Entonces, esto fue la primera, digamos, alarma en la que algo de software, algo virtual, por así decirlo, ya podía dañar cosas físicas. ¿Por qué? Porque al modificar el uso y el control de esas centrifugadoras, pues se dañó y se rompieron. Esto fue, lo que hizo fue eliminó algunas, digamos, restricciones de seguridad dentro de los PLCs. Después se supo que fue algo de política, etcétera, ¿no? Pero bueno, lo importante que es el virus fue el primero que mostró que algo informático puede realizar o puede generar problemas, digamos, físicos, ¿no? Después, en el 2007, otro caso algo conocido fue Tritón y este todavía es el otro. Al final se descubrió que fue un virus hecho por algunos gobiernos con cosas, como les decía, políticas. Pero el problema de este otro virus es que aunque no haya evidencia, digamos, lo 100% segura, todo apunta a que fue un problema de phishing. El phishing a grandes rasgos es el típico correo que nos llegaba de te ganaste un iPhone, pícale aquí, ese mero, ¿no? Entonces, ustedes podrán pensar que es muy obvio que no me gané un iPhone, ¿no? Pero desgraciadamente, entre el 70 y el 80% de los ataques cibernéticos ocurren por phishing. Ni siquiera es que, es que hackearon la clave, el servidor, interrumpieron. No, desgraciadamente la mayoría es alguien dentro de alguna empresa que le picó a donde no tenía que picarle, ¿no? Entonces, justamente este malware entró así, a través de phishing. ¿Qué es lo que hizo? Entró a algunas computadoras dentro de lo que era la industria, se guardó y atacó unos servidores justamente de control. Entonces, lo que hizo esto es que manipulaba el sistema de protección en algunas plantas petroquímicas, así como se pueden imaginar, Pemex, por ejemplo, eliminaba partes de seguridad. Entonces, obviamente eso pudo llegar a causar, porque se detectó con tiempo, problemas mucho más grandes, ¿no? Que explote algo, problemas ya incluso de muerte, ¿no? A los trabajadores que estaban ahí. Entonces, este específicamente atacó a una versión del software que tenían en ese programa. Entonces, cada vez se fue viendo que ya eran más desarrollados tecnológicamente, sobre todo en el sentido en el que no se pudieran descubrir. Después hubo uno que se llamó, o le llamaron Black Energy. Esto pasó en Ucrania, y esta captura de pantalla que les pongo aquí, literal, es con lo que ellos entraron. Lo mismo, algo de phishing, a una persona dentro de la empresa le llegó un correo que o sea, era un Excel, curiosamente era un macro a través de un macro de Excel, para que no crean que tiene que ser algo muy complicado, a través de cosas muy simples, pueden llegar a atacar. Y la persona ni siquiera sabía este idioma, que creo que es ruso, pero literal aquí en el Excel dice que no le piquen al botón de abajo. ¿Y qué hicieron? Pues le picaron, y eres casi, casi como una prueba, ¿no? Entonces, es lo que les digo, desgraciadamente la mayor parte de ciberseguridad, ustedes creerán que alguien en ciberseguridad se dedica a diseñar software súper, como en las películas, ¿no? De lo voy a contrarrestar. No, desgraciadamente la mayoría de la parte de ciberseguridad es hacer que la gente no le dé clic a estos correos. Entonces, bueno, ¿qué hizo esto? Que ya es algo más, ya no se atacó una empresa, ya no se atacó, etcétera, ¿no? Aquí se atacó a la red eléctrica de Ucrania. Entonces, justamente lo que causó fue unos bloqueos masivos dentro, o durante, perdón, el invierno. Entonces, como sabrán allá en esos países, pues el invierno es fuerte, ¿no? Y muchas veces las calefactores que usan allá son eléctricos. Entonces, esto causó un problema bastante grande. ¿Qué usaron? Pues simplemente sistemas spear phishing, que prácticamente es lo que les acabo de decir, mandar un correo para que la gente caiga. Y este fue el primer ataque que causó, digamos, ya un daño a gran escala a lo que es una ciudad entera, una civilización, bueno, una sociedad, por así decirlo, ¿no? Entonces, cada vez se van haciendo más complejos estos ataques, y cada vez van teniendo consecuencias más peligrosas, ¿no? Obviamente, es a lo que hay que tener cuidado. Entonces, esos fueron algunos de los casos. Si ustedes buscan en internet, hay muchísimos más, y otros que ni siquiera nos hemos enterado. Porque obviamente una empresa a la que recibe un ataque cibernético, pues no lo va a estar publicando tan fácil, ¿no? Generalmente lo publican cuando los cachan. ¿Por qué? Pues pierden confianza, etcétera, ¿no? Entonces, ¿qué es lo que podemos hacer nosotros que estamos, o en general, involucrados en la parte de la automatización? Porque no queremos que la automatización que nosotros hagamos sea el punto débil por el que entró, digámoslo así, un ciberataque, ¿no? Entonces, bueno, quedamos que el ISS y el SCADA, que son prácticamente los sistemas que controlan, o así le llamamos en la automatización a los sistemas completos, son los que están en riesgo, ¿no? Entonces, todos estos casos que les mostré anteriormente son ataques que ya no es hipotéticamente que nos pueden atacar, sino que es una realidad, ¿no? Entonces, estos sistemas ahora están expuestos a la parte de redes e internet, ya no está aislado, ¿no? Entonces, ese es el gran problema, que antes una empresa tenía su propia red interna y jamás salía o entraba información. Ahorita ya no es posible eso, ¿no? Sobre todo empresas muy grandes que pues, tienen que mover mucha información, logística, etcétera, ¿no? Entonces fue cuando se necesitó, se demostró que se necesitaban estrategias de ciberseguridad para poder proteger estos sistemas. Entonces, el problema es que la mayoría de los protocolos, ya ahorita ya han cambiado, pero la mayoría de los protocolos iniciales que se utilizaban para todo lo que es la comunicación, etcétera, en el momento en el que se diseñaron, no se diseñaron pensando en seguridad. Se diseñaron pensando en qué, en que fueran útiles y resolvieran el problema en ese momento. O sea, algunos tipos de protocolos que se usan mucho en la industria, en general, Modbus, DNP3, no están encriptados o no necesitan autenticación. Es decir, prácticamente cualquier persona con acceso a la computadora en la que está instalado el software puede acceder y modificar las cosas. Y no solamente eso, hablando de la encriptación, que a grandes rasgos es hacer que alguien no pueda leer lo que estamos mandando o escribiendo, es como cambiarle el idioma, por así decirlo, es una de las, digamos, maneras más potentes y simples al mismo tiempo de proteger lo que es la información. Entonces, todos estos protocolos no manejan esto porque en el momento en el que fueron propuestos no nos interesaba la seguridad. Entonces, fueron diseñados para sistemas cerrados, ¿no? Sistemas que no iban a tener conexión. Y estos sistemas, que pues, se quedaron, digámoslo, un poco antiguos, son fáciles de recibir ataques como lo son la intercepción de comandos, la suplantación de identidades, de que yo le hago crear el sistema que soy un dispositivo que realmente no lo soy, y así, ¿no? Por ejemplo, algunos comandos Modbus pueden ser abiertos O cerrar válvulas, por ejemplo, sin siquiera autenticación. Yo le puedo mandar un comando falso a la computadora que lo maneja y va a hacer la indicación sin siquiera preguntarme quién soy. Mientras yo lo pueda andar al lugar correcto, por así decirlo, con eso es suficiente para que ocurra. Entonces, justamente uno de los mayores problemas, como les decía hace rato, de esta parte de la automatización son los dispositivos legacy, que son los más antiguos. La ventaja es que nosotros pues trabajamos con dispositivos un poquito más nuevos, ¿no? Que no sufren con estos problemas. Pero justamente si estamos trabajando con dispositivos nuevos, hay que tener cuidado que no heredemos estos problemas legacy de lo que es autenticación, seguridad, etcétera, ¿no? Ahora, este es uno de los que, como les decía, los problemas más comunes dentro de la seguridad, que son los errores humanos y las malas prácticas. ¿Cuál es una de las prácticas más malas y que aunque ustedes no lo crean ocurre ya a nivel empresarial o nivel industrial? Es el uso de contraseñas default. Que compré un PLC que ya trae un poco de seguridad, que ya trae, necesito un usuario y contraseña, pero jamás se lo cambié. Le dejé el de por defecto que es usuario admin, contraseña admin. Entonces, pues obviamente los atacantes van a ser las primeras cuentas con las que prueben, ¿no? Entonces, pues no cambiar este tipo de cosas es muy peligroso, ¿no? Servicios expuestos sin protección, es decir, que no tengamos niveles de protección o que ni siquiera los activemos. ¿Por qué? Porque son prácticas que no estamos realizando de manera correcta, ¿no? Entonces, por ejemplo, algunos PLC Siemens que dejan con las llaves por defecto, que por ejemplo vienen en manuales. Entonces, cualquier persona que revise, perdón, un manual PLC de algún que detecte que está instalado, pues va a encontrar las contraseñas por defecto y las va a poder utilizar. Entonces, algún ejemplo práctico, pues alguna empresa que integre SCADA, que como les comentaba es el sistema que recaba la información, la muestra y hace el control, en una empresa, pues que esté conectado de manera remota para hacer monitoreo. Entonces, ahí es de la primera cosa que, digamos, estamos poniendo en riesgo al ponerlo en lo que es la red, ¿no? La red en general, el internet, etcétera, ¿no? Usar protocolos Modbus sin encriptación, por ejemplo, tener accesos remotos con credenciales débiles, es decir, que yo construya o diseñe, por ejemplo, un sistema, ustedes hacen alguna automatización, algún robot, lo que sea, y lo quieren dejar en algún lugar utilizándolo, ¿no? Pero quieren que una persona desde su oficina, lo que sea, lo pueda controlar y hacen una red, lo conectan Wi-Fi, como ustedes quieran, ¿no? Si todos esos datos que ustedes están mandando no los protegen de cierta manera, pues obviamente estamos otra vez poniendo en riesgo toda esta parte, ¿no? Entonces, como resultado, ¿qué puede pasar de estos ataques? Como hemos comentado, pues que se detenga la producción de lo que ustedes quieran que esté haciendo, o de un robot, de un control, de cualquier cosa que estemos automatizando, pues que se detenga, ¿no? Entonces, si nosotros estimamos un sistema automático para un invernadero, lo que ustedes quieran, se detiene, pues ya no está haciendo lo que queremos. Y si no nos damos cuenta, pues peor, ¿no? Porque vamos a llegar y vamos a creer que se estuvo controlando y no. Obviamente pérdidas económicas y como les comentaba en algunos de los ejemplos, pues algunos posibles daños ya físicos en algunos aparatos, etcétera, ¿no? Entonces, esto, como les comentaba, para ir avanzando más rápido, esta parte que se diseñó en aquel momento, se diseñó para disponibilidad, no para seguridad. Entonces, la primera parte en la que ustedes pueden hacer defensa es hacer defensa por capas. Es decir, ustedes pueden decir, pues existe la encriptación, lo voy a encriptar. Ok, esa sería una capa. Pero si aparte vamos agregando más capas de protección, pues obviamente cada capa va poniéndole, digámoslo así, una dificultad extra al atacante. Entonces, si el atacante se encuentra con 17 capas, pues va a decir, a lo mejor no me conviene dedicarle tiempo a atacar esto, ¿no? Entonces, siempre digamos que nunca es suficiente. Mientras más capas de protección agreguemos, siempre va a ser mejor. Y incluso siempre se considera que hayas que hacer protección tanto lógica, es decir, software, etcétera, como física. Porque como se puedan imaginar, y eso a lo mejor es un poco más obvio, nosotros podemos proteger una computadora de un ataque externo, etcétera. Pero si literal dejamos el servidor de una empresa sin llave, abierto, casi casi con una flecha que diga aquí está nuestro servidor, literalmente físicamente alguien puede ir al servidor, conectar una memoria USB y hacer lo que quiera, ¿no? Entonces ya no solamente es de manera virtual, también de manera física, que a veces no lo tenemos en cuenta. ¿Qué podemos hacer nosotros en nuestro robot, en nuestra práctica, etcétera, para que físicamente nadie pueda llegar y con un botón destrozar nuestro robot, por ejemplo, nuestra automatización, ¿no? Entonces, todas las capas que nosotros agreguemos de protección a lo que es nuestra automatización, pues siempre le va a poner un poco más difícil al atacante el poder llegar a su objetivo, ¿no? Que es nuestro sistema. Entonces, otra parte importante es que segmentar la red industrial. No sé si a algunos de ustedes se les ha tocado visitar alguna parte industrial, pero lo ideal sería que ustedes si llegan, por ejemplo, no sé, voy a poner un ejemplo, a Walmart, ven que Walmart da internet gratis. ¿Ustedes creen que la misma red que les da el internet gratis sea la que ellos dicen para sus servidores? Obviamente no, ¿verdad? No te van a dar el acceso a su red. Pues como lo podrán imaginar, hay empresas que sí hacen ese tipo de cosas. Utilizar la misma red, digámoslo así, para el público o para cosas más externas para internet y la misma red que usan para servidores. Entonces, esta parte de segmentar la red hace la división de, ok, esta red es interna, es industrial, tiene seguridad, etcétera, y hay otra red que no es necesario asegurar. Entonces lo dividimos en zonas para que pueda ser mejor protegido. Luego separamos los procesos críticos, todo lo que es la parte interna, la protección, los datos que salen, de la red corporativa, por así decirlo, ¿no? Lo que se usa para todo lo demás. ¿Cuáles son los procedimientos? Obviamente limitamos, perdón, el acceso al malware a nuestra red, facilitamos la detección de anomalías, porque otro problema de la seguridad en la automatización es que a lo mejor, como en la parte anterior, dijimos, yo agregué 5 capas, las agregué, estoy seguro que son súper seguras, valga la redundancia, pero si no estamos monitorizando lo que está pasando, sería un problema, ¿no? Si yo hice un robot que está diseñado para trabajar, por ejemplo, de 8 a 8 y no lo monitorizo, no me doy cuenta que a las 12 de la noche alguien lo enciende y hace cosas. Entonces, si estamos monitorizando, también es una manera muy importante de ver que algo no está ocurriendo bien. Por ejemplo, como justamente esto, separar la parte de la red de control con el management, me refiero más a la parte, digamos, corporativa, empresarial, de la red de control, de lo que controla, por ejemplo, todos los brazos, etcétera, ¿no? Otra parte, que todo esto es la protección, digamos, activa, es decir, hay que protegernos antes de que ocurra el accidente, es el Zero Trust Model, es decir, no confiar en nadie, prácticamente ni siquiera en uno mismo, ¿no? Entonces, justamente esta parte o este modelo tiene, digámoslo así como lema, el Never Trust, Always Verificar. Entonces,
Te
siempre,
quedan 5 minutos.
ok, entonces siempre vamos a, nadie, no confiar en ningún usuario, siempre vamos a verificar que eres el que tú dices ser. Entonces, ¿cuáles son las partes importantes de esto? Autentificar continuamente tanto usuarios como dispositivos, hacer políticas basadas en identificación, que te estés tú continuamente haciendo login y revisar constantemente privilegios, que por ejemplo, a lo mejor la persona que está en recepción no tenga privilegios para la base de datos de producción, por ejemplo, ¿no? Hay que segmentar esa parte muy bien. Y la vigilancia, que era lo que les decía ahorita, es importante estar detectando o estar verificando los sistemas. ¿Por qué? Porque podemos detectar justamente comandos sospechosos, cambios en las configuraciones de los PLCs o de los FPGAs o de cualquier dispositivo que usemos para control y algunas anomalías en los patrones de comunicación que tienen los dispositivos. Todo esto nos va a permitir tener una idea de que algo está ocurriendo. Entonces, como les decía, no solamente basta con el prevenir, también siempre hay que estar monitorizando. Hacer el mínimo o permitir el mínimo acceso, lo mismo que les decía ahorita, si una persona está contratada para hacer la recepción, que su computadora o su usuario no tenga acceso a cosas más importantes. Voy un poquito más rápido y prepararse para los incidentes, es decir, no hay ninguna manera, ningún modelo que sea 100% efectivo, siempre se puede encontrar la manera de, de, de romperlo, digámoslo así, las partes seguras. Entonces, siempre hay que tener planes de respuesta, backups, a veces no hacemos backups tan constantes, no estamos acostumbrados, y ya no es que el dispositivo solamente pueda reiniciarse o apagarse. Si nos atacan y se llevan toda la información, pues hay que tener backups, ¿no? ¿Cuál es el objetivo? Minimizar el daño. Ok, no logramos que nos atacaran, no logramos evitar que nos atacaran, perdón. ¿Cuál podemos hacer? La manera en que haya el menor daño posible. Y otra es aplicar las nuevas, digamos, tecnologías, que es parte de todo lo que es IA, etcétera, algunos algoritmos de machine learning, etcétera, para poder hacer la detección. Porque muchas veces, aunque nosotros estamos vigilando, no nos damos cuenta que estamos atacando, que nos están atacando, perdón. Entonces, toda esta parte de inteligencia artificial y de todo lo que es machine learning, podemos ponerlo a revisar comandos de PLC, tráfico de lo que es la red, etcétera, ¿no? Rápidamente, esto es algo que se usa mucho y es como poner un señuelo o un equipo señuelo para ver que los atacantes ataquen a ese justamente señuelo. ¿Y de qué sirve eso? Pues para aprender técnicas de cómo es el ataque de los que quieren atacar, de los atacantes. Entonces ponemos un señuelo, lo atacan, no hacen daño, pero nosotros podemos observar cómo hicieron ese ataque y aprender de cómo ellos atacan. Y por último, también no solamente automatizamos en el sistema, también podemos automatizar en la respuesta. ¿Para qué? Para que nosotros no tengamos que estar revisando todo, sino que automáticamente haya cosas que se defiendan en lo que es el sistema, valga la redundancia, automático, ¿no? ¿Y cuáles son, digamos, el futuro, por así decirlo, de esta parte de la seguridad en la automatización? Pues una es incrementar la adopción de toda esta parte de inteligencia artificial para poder predecir todo lo que son los ataques, integrar más esta parte de Zero Trust en toda la parte operativa, desarrollar e incrementar, digamos así, señuelos más sofisticados para poder de ahí obtener información de cómo es que atacan, colaborar, esto ya es un poco más a nivel, digamos, política, pero es colaborar un poco más en todo lo que es el sector público con el privado y hacer, digamos, un frente unificado, por así decirlo, ¿no? Y pues es importante, sobre todo, que estemos conscientes de que es una parte importante de la automatización el que nuestros sistemas sean seguros. Y muchas gracias.
Thank you. Do you have some questions to the speaker? Yeah.
Hola.
De ataque por phishing.
Uh-huh.
Y entonces, pues ahí veíamos que el factor humano pues era el principal, ¿no?
De los más.
Y entonces, ¿qué nos recomendarías hacer para pues prevenir esto? Ya que pues las medidas de seguridad a veces pues están analizando protocolos, autenticación,
Claro.
algunas capas no permiten, pero por ejemplo, ahí en ese caso de que una persona pues ya le llegó el enlace, ¿no? Mira, descarga aquí memoria RAM y a veces pues nosotros nos da risa, ¿no?
Sí,
Decimos,
claro.
¿cómo va a descargar RAM? Pero hay personas que realmente dicen, ah, pues aquí ya me salió un mensaje que necesito RAM, que también es por culpa de phishing, y le da clic, ¿no? Y entonces, ¿tú qué nos recomendarías para protegernos acerca de eso?
Ahí hay como dos partes principales. Una es la concientización. Obviamente, ya cuando una persona, bueno, cuando una empresa sabe que puede tener ese tipo de riesgos, tiene que concientizar a sus trabajadores, así como los capacitan para, digamos, lo que van a hacer, tienen que capacitarlos para ese tipo de cosas, sobre todo gente que va a tener acceso a computadoras, etcétera, ¿no? Esa parte tecnológica. La capacitación es clave, porque va a haber gente que cree que darle clic a eso y que no pasa nada, ¿sí me entienden? Como de informarles del riesgo que puede ocurrir. Y la otra es, y muy importante, es tener políticas. ¿Cuál es, por ejemplo, una política? Ok, a tu correo corporativo, por ejemplo, nuestro correo de la UAP, si te llega cualquier otro correo que no sea @buap.com.mx, ni siquiera lo abres. Entonces, hay ciertas políticas que tú tienes que decirle a tus empleados, casi casi pegárselas al lado del monitor, que diga, no abrir correos con extensión que no sea conocida, por ejemplo, o no compartir contraseñas, o cambiar tu contraseña cada 3 meses. Entonces, si tú diseñas un buen, digamos, plan de políticas que tienes que estar seguro, obviamente, que ellos lo apliquen lo más posible, nunca vamos a poder estar atrás de ellos viendo que realmente lo cumplan, ¿verdad? Pero que ellos conozcan las políticas para que las puedan aplicar, porque muchas veces sí es obviamente que no tienen como esa malicia, pero otro también es desconocimiento, no saben que esas cosas pueden ocurrir. Sobre todo esas dos, tenerlos como capacitados y generar un buen sistema de políticas para que ellos sepan qué es lo que no tienen que hacer y que sí. De nada.
Anyone? No? Ah, okay.
Sí, bueno, hablabas sobre phishing, pero ¿cuáles son los otros tipos de ciberataque más comunes o que generan más vulnerabilidades en las empresas?
Del que yo, digamos, lo he habido investigado, es uno que se llama, bueno, son dos, uno que es suplantación de identidad, es decir, yo simulo que soy un dispositivo que no soy, y no solamente puede ser identidad en cuanto a dispositivo, sino identidad en cuanto a credenciales. Yo simulo que soy un administrador, yo simulo que soy tal cosa. Y no solamente con su contraseña y con su usuario y contraseña, sino Yo sé que tú como servidor estás esperando que yo te dé ciertos mensajes. Entonces yo puedo descifrar esos mensajes y sé, digamos, cómo funcionan bases de datos, etcétera, y estoy suplantando la identidad de alguien que pueda administrar el control. Esa es una. Y otra, que va más o menos por el mismo sentido, es uno que se llama man in the middle, que es como el hombre a la mitad. O sea, hay una comunicación, por ejemplo, yo saco mi celular y quiero revisar mi robot, pero alguien intercepta la comunicación entre mi dispositivo y al que me quiero comunicar. Entonces, ese es uno de los más, entre comillas, sencillos de evitar, porque si usamos encriptación ya no pasa eso. ¿Por qué? Porque no solamente la encriptación me da o me protege para que lean mis datos, sino que la encriptación también sirve para saber si con el que yo me estoy comunicando es el que realmente dice ser. Entonces, aparte del phishing, que es como el 80%, esos dos son los casos más comunes en lo que es la industria en general. Gracias.
Okay, well, thank you for your presentation, please. Applause. And we will give you the acknowledgement.
Thank you.
A little gift.
Thank you.
Okay. Okay, thank you. We will continue now with Dr. Mónica Palmar with the title of the speak, a security framework for storage optimization for IoT application using secured hash algorithm. Next, I will give a little moments to be prepared. Go. Okay, is the presentation is ready? Okay. Then I will give you her academic overview. Dr. Monica holds a B.Tech in Electronics and Communication Engineering in the year 2006 and M.Tech in Communication Systems in 2008 and a PhD in Electronics and Communication Engineering in 2022. She currently serves as the Associate Director, IQAC, and Associate Professor, School of Engineering and Technology at Chitkara University. Himachal Pradesh, in India. Dr. Monica has over 15 years of experience in teaching and administrative tasks. She is actively involved in research and has 12 patents to her credit. Her research interests include Internet of Things, satellite communication, wireless sensor networks, Internet of Vehicles, security and privacy of IoT application, blockchain technology, machine learning, and artificial intelligence. Okay, please give an applause.
Thank you, Dr. Arora, for my introduction. Thank you, everyone. And good morning, one and all present here. Sorry, I'll be speaking in English because I do not know Spanish much. Sorry. So I'll be presenting a security framework for storage optimization of IoT application using secured hash algorithm. This was my PhD thesis topic. I'll not be covering my whole thesis. It's just a small portion of my thesis. So I'll be covering that. Okay. And I'm from Chitkara University, that is in India. So I'll be covering the introduction, what is the motivation for my research, what are the challenges faced in Internet of Things, that is IoT, the research gaps, research objective, my contribution, my methodology, and the framework which I've proposed. Okay. Okay, so we already know the Internet of Things is getting many pace during the last 10 years. And with the emergence of wireless technology, we are having Internet of Things, we are having artificial intelligence, we are having machine learnings, but there are many problems with the IoT as well. For example, due to the advancement, the internet is being used to share the data. So data is the major problem, or we can say it's a bottleneck here in IoT or in any wireless technology. So there are many Internet of Things devices that are connected to each other, plus the data that is generated by the IoT devices are huge. So our main bottleneck is data, huge amount of data, and the storage capacity where we are going to store that huge amount of data. So it is required to provide a solution for various network related issues that is related directly or indirectly to the IoT. So as you can see here, this is the progression of the number of connected devices. So from year 2015 to 2025, you can see the exponential graph, and it is the number of interconnected devices that are interrelated to each other. And in 2015, we have just 15.4 billion devices that are connected to each other. But as we can see here in 2025, it's increased rapidly and it is 75.4 billion devices. And it's continuously increasing day by day. Now also as we are talking, so these devices, the interconnected devices are increasing. So you can see here that if the number of devices that are connected to each other are increasing, that's mean that data that is stored onto the cloud or any devices is increasing also. And this was the Google search trends for 2020-21 when I was doing my PhD. So at that time, you can see the Google search trends for Internet of Things and blockchain technology, IoT security, and storage optimization. And now if we talk about the today's time, it's for April 2025. We can see this is the market enterprise of IoT, and the rupees are spending in billion. So that area, this one is showing the actual value in billions in rupees. And this showing the forecast. And there is a very minimum difference in between the actual and the forecast value. So whatever we are forecasting here is actually the actual value in billions. And this is in billions in rupees or in dollars. So my motivation is first, the enormous data that is being produced by the Internet of Things. And cloud computing is also for the virtual storage of the data, but we are also talking about the data storage physical mode while the sensor being used. Also the storage optimization, we have to optimize the storage also, and there are security concern in the Internet of Things as well. So as a result, the IoT must be designed to minimize the impact of the massive data on the other system that use wireless, and in some cases it is wired media. So if we talk about the need of storage optimization, it is basically for practical performance because of the low cost, because of the low scalability. And if we talk about the need for security, IoT security, it's basically used for healthcare, hospitality, government, retail, transportation, and manufacturing. If we talk about the layered architecture, I'll quickly just showcase all the layered architecture of the IoT. It's having perception layer where we are having all the sensor, all the hardware devices that are connected to each other. Then we have the network layer. It is having the gateway and the networking communication in between the network layer. In middleware layer, we are having the processing unit, for example, embedded system, microcontrollers, microprocessors, likewise. And in application, we have the user-defined values. So this is the layered architecture. And if we talk about the IoT security, every layer is having different problems, different attacks, different threats. So if we talk about perception, it is having different layers of attack. If we talk about middleware or application, it is having different threats. So in my PhD thesis, I have covered perception layer and network layer threats. I have compared those threats, and I have reduced those threats in my thesis. Okay, so there are challenges in the field of IoT as well. So if we talk about the scalability challenge, there are many devices connected in billions in number. So we have to face the scalability challenge over here. Then there is a cloud storage challenge also. And nowadays we are facing this challenge more, cloud storage. And there is obviously a security challenge in IoT devices. There is a design challenge with the IoT devices because every device that are connected to each other are having different design values. So we have to face this design challenge as well. Interoperability is another challenge. Congestion, where there is a more traffic, you have to face the congestion problem as well. So these are some of the challenges in Internet of Things. As I have discussed before, that every layer is having different attacks. So these are the attacks on physical layer. These are not all, these are some of the attacks. In network layer, we are having this attack, for example, sinkhole, unauthorized access, phishing site attack, DOS attacks like that. And these are the attacks in middleware layer. There are many attacks on middleware layer because it is a kind of communication in between the first layer and the last layer, or you can say the transmitter and the receiver. So it is acting like a communication link between the transmitter and the receiver. So these are some of the challenges in application layer. For example, trust management, authentication, malicious scripts, policy. So I have covered these attacks. I have just compared these attacks and how we can reduce these attacks by using the framework. So I have introduced blockchain. I'm sorry. Yeah, so I have used blockchain as a solution for the IoT threats. IoT as a field are having many attacks, many threats on each layer. We have discussed this. So I have used blockchain technology, blockchain architecture in my IoT sensors at the physical level. So it's the interconnection of block. These are the blocks, first block, second block, third block, fourth block, for example. So the first block is always known as the genesis block in blockchain. And the second block is this block, which is interrelated to the first block using its previous hash. Like we can see here, every block is having a hash. And hash is a unique identifier that is unique to every block. So we can say hash acts as a unique fingerprint for every block. So if we talk about the blocks, first block, that is a genesis block, will not be having any previous hash because it is the first block. So it will be 0 over here. And hash, the unique value of hash for block number 1 is 2ZB1. And it is connected to block 2. Block 2 will be having its hash, that is previous value of this block 3 hash. And the previous hash for block 2 will be 2ZB1. So you can see it's common with block 3, and this value is common with block 1. So these are interrelated. So if any attacks happen at block 1, if some user wants to change any data of block 1, immediately the hash will change, and the blockchain will be knowing that there is a problem in block number 2 or block number 3, so on, right? So this is the concept of using blockchain in IoT. So these are some of the challenges in IoT, and these are the challenges, and these are the possible blockchain solution for those challenges. For example, privacy in IoT devices, we can reduce this with the help of blockchain technology. So these are some of the papers I have referred to. So my objective, these are not all of the objectives, these are just the glimpse, just the 3 objectives. So my first objective was to evaluate different type of secured hash algorithm used in blockchain model and to do the comparative analysis for the threats of IoT. My second objective was to propose and implement a framework for IoT devices and application by using hash algorithm, which was selected here, and for storage optimization. My third was performance analysis of proposed framework of IoT security and data optimization. So these are the research objective for the previous slides. This is my research methodology. I have done the comparative analysis of SHA. Then I have selected one SHA out of those secured hash algorithms. Then I have done hashing based on the data transaction for IoT applications. And then I have done the storage and the space optimization based on that. Then I have done the consensus routing protocol for improving the security of IoT devices. I have used network model, cluster head selection, data transmission, then clustering routing protocol and malicious node detected in that process. And finally, I have compared the performance with the another authors. So my research contribution, I have used the simulation-based comparative analysis of SHA. For that, I have compared MD5, SHA1, SHA2, and SHA3 families secured hash algorithm. And I have done the experimentation on Java Eclipse using 6 iteration, 6 steps, 3 for small sequence and 3 for the large sequence. And then I have designed and simulating secured and optimized framework for IoT application. For that, I have used Node MCU ESP8266 Wi-Fi module with the many controllers, and I have used 10 sensors for this. And then at last, I have simulating cluster routing algorithm to enhance the security. And for this, I have used IoT sensor on the blockchain technology and using cloud on Linux Ubuntu operating system. So these are the research methodology step. I have used NS 3.27 using Ubuntu software. So for the comparative analysis of the hash algorithm, I have used 3 methods. First is on the basis of output size in bits. Second is on the basis of file size and time. And third, on the basis of the speed performance. So based on this, I have compared these together. And out of this, this was the result. And for security, for speed, I have chosen SHA-256 algorithm for my Internet of Things protocol. So you can say here, SHA is having more features as compared to the other ones, SHA2 family, SHA3 family, SHA1 family, and MD5. So for my PhD thesis, I have used SHA-256. This is the comparative analysis for file size versus time. In this case, SHA3 family is showing the values as compared to SHA2 and SHA1 family. But I have used SHA2 because for me, security matters the most, irrespective of the time. So I have compared speed performance comparison on MD5, SHA1, SHA-256, SHA-512. And for that, I have used 64-bit microprocessor, Windows 10 with this frequency. I have used 16 GB RAM. And 5 measurements were made for each case with an average value is calculated. For example, for this case, I have used hash time calculation for 36 character in length with no extra time. For case 2, 49 character in length, but with cached UUID. Then case 3 is hash for 49 character in length with new UUID generated. And case 4 with 72 characters. So, case 5, 85 characters. Case 6, 85, but length is addition to new UUID. So the comparison and speed performance of hashing algorithm is done. And for speed also, I am using SHA-256 also with the security, with the speed as well. So these are some of the snapshots. These are for small and large sequences. So in comparison and speed performance of hash algorithm, SHA-512 was better. But again, I have to choose in between SHA-256 and SHA-512. So for security, I have used SHA-256. For speed, sometime I have used SHA-512. So this was the hashing. This was the phase 1, hashing-based data transaction and optimized storage for IoT devices. I have a sensor unit having 10 sensors. I have a data acquisition and processing unit, and then I have a data transaction unit. That is module 3. So for module sensor, for this particular phase, I have used 6 sensors. I have used dust concentration sensor, voltage level sensor, water level sensor, temperature, humidity, and air quality sensor. So these just 6 sensors just to get to know whether SHA-512 is better or SHA-216 is better. So I have used that. So module 2 describe a data acquisition and processing unit. For that, I have used microcontroller node MCU ESP8266. I have used many data compression techniques at the transmitter. I have used secured hash algorithm, and then I have used the decompression unit at the receiver side. So this was just the first phase of my hardware unit where all the sensors are interconnected to each other. And I have taken the reading for 50 days just to get to know about the speed and security of IoT. Phase 1, module 3 was data transaction onto the cloud. So I have collected the data from the sensor unit, then I have data transaction onto the cloud. I have used ThinkSpeak Cloud for this, and now I'm working on AWS Cloud. And then I have done the analysis and I have retrieved the data from the cloud. So this is the sample data. This is just the 10 values out of 100 values. It's the data on the ThinkSpeak Cloud. So this is the compression technique where the system initializes, where it is received from the IoT sensors. I have to check whether the IoT device is authentic or not. I have to check the security of the IoT device here using SHA 216. And then I have, if it is no, discard the data. If it is yes, it will do the certain operations. So our main point is to store the IoT sensor value onto the blockchain here. So this is the decompression technique at the receiver side where I'm getting the data again at the IoT values in the Excel CSV file. This is the algorithm for data compression. This is the algorithm for decompression. On Eclipse Workspace, this is just a snapshot how I have used the IoT sensor and how I have used the SHA algorithm inside it. This is for decryption values. So storage optimization, this is the output. This is just for the 10 outputs. So hardly matter I am giving 100 or 1000 of the values over here, I'll still be getting the same hash. So this is the main outcome of my issues over here with the IoT and IoT devices connected to each other. And this is the outcome. The data recovering from the blockchain is this, and data before sending to the blockchain is this. Next is the space optimization. For space optimization, I have just for the IoT application for size in kilobytes. First case I have taken with 600 sensor values. Second case was with 1900 sensor values. And third case was 3800 sensor values for 50 days. So for this particular thing, for this conclusion, it's 50% compression ratio was achieved in the first step. If you talk about the phase 2 framework for enhancing the security, I have used consensus routing protocol to improve the security, where I have detected the malicious node and I have done the performance comparison. For this, my parameters were network lifetime, scalability, mean time delay, throughput, data packet loss, delivery ratio, and overhead latencies. So these are my parameters for my research. I have used this software, Java Eclipse IDE 2019, simulator NS 3.27. So this is the secured clustering routing protocol where I have started with the network framework, which I have proposed, and random selection of node was taken into consideration. And after that, I have detected the malicious or the intruder node at the blockchain. So this is just the routing algorithm for the first step, malicious node detection. The main point is I have used the Byzantine agreement in my thesis to detect the suspicious node at every point of the blocks, wherever it is in the IoT applications. This is the Byzantine categorization. So I have selection phase, I have cluster head selection phase, I have node classification phase, and then the malicious node detection selection phase. For this, I have used the hybrid fuzzy possibility. C means clustering HFCM. It is used for optimizing the various cluster in the network, and at the same time, it will show you the malicious node in the particular IoT framework. So HFPCM is employed by proposed cluster routing protocol in order to construct the clusters in the network. So I have made many clusters in IoT applications. This is some of the equations which I have used. And this is the code structure of NS3 simulator for execution of the program. So I have first insert the new device, then the inquiry, then the block mining I have done. I have created a block. Then I have checked whether the block is validated for IoT or not, and then exit the program. These are some of the snapshot by the receiving nodes. Some snapshots of results. So first parameter was throughput. You can see throughput of HFPCM algorithm, which I proposed. This is this result. Later on, I'll share what is the throughput of the base papers. So another parameter is packet loss. You can see over here, if I have increased the number of node, it becomes constant. It is decreasing with this packet loss in percentage. For bandwidth, it is the number of node for the packet delivery ratio in percentage. You can see it's growing rapidly and exponentially. For overhead latency, this was the result when the number of nodes and mean delay in seconds for the nodes. And if there are a number of more blocks, it will decrease. The delay is less in my proposed algorithm. For scalability, so yes, I have compared my research proposal with this existing algorithm. Algorithm 1 was routing protocol algorithm for Internet of Things, and algorithm 2 was predicting latency algorithm for blockchain-based technology using architectural modeling. So I have compared with these two, and I found that comparison in terms of mean delay, mine was performing better. Also for data packet delivery ratio, it was better. Minus this green one. This one is my proposed one, and these two are the base one. So this is for throughput, this is for packet loss, and this is the comparison with the existing algorithm. Technique applied for this is they have used the consensus POW, proof of work. I have used HFPCM hybrid fuzzy model. And for throughput, I have high fault tolerance. In this, it is based on the hash algorithm. And overhead latency, it's high priority and low latency, but for my case, I have worked upon the security. So this is just a comparison with the existing algorithms. So in conclusion, I have found that IoT security, the hash must be selected accurately, and it is found that MD5 is although faster as compared to SHA-1 family, but I have chosen SHA-2 family because of the security. In addition, SHA-1 is slower than SHA-256 for smaller string, and if we are going with the larger string, it is fastest. Also, SHA-1 is lower than SHA-256, which is 2.59% error rate for larger string. So I have worked with SHA-256. Also, we have optimized the storage by 50% compression ratio with secured data onto the blockchain technology. Hybrid crypto hash function is used for security enhancement here for IoT as well. This is my future scope. I have worked with on the first layer and the second layer of IoT. Now my future scope is working on the third layer and the fourth layer, also on the hardware layer. For example, he mentioned SCADA, so maybe that I'll work upon. These are some of the references for my work. So thank you so much.
Thanks a lot for your presentation. Any questions?
I know it's a bit boring for you because in English.
Ah, they can.
Well, thank you for your presentation. Well, at some point you talk about you have two hash algorithms. I think one is MD5 and SMA, I think.
SHA, yes.
What is the difference between these two algorithms?
See, MD5 is older version of hash algorithm, but SHA is a new kind of technology. And also there are many attacks mentioned before in the past for MD5. There are many attacks, but SHA, there are no attacks since now. So it's older, it's newer, that's it. Yes.
Anyone? Please.
Hello. You test your algorithm in Java in a
Yes.
computer,
Yes.
but what about the difference between a lot of device, the power of calculate of that devices?
Um,
How do you think the difference between Arduino versus FPGA or
yes.
etc.?
Yeah, that's my future scope only, that I have to use FPGA as well. In my thesis also, I have worked with little bit with FPGA. When you are concerning about more of hardware security, you go with FPGA. And if you are more concerned about the software, then you are going with SHA, which I have used. So this is my future scope, to work with FPGA. Yeah.
More question, please.
What was your challenge when you have the process to compression the information in 50%?
Yes.
And why do you use the blockchain method to front the security problem?
Okay. See, there are many challenges with the IoT devices, and there are more challenge with the IoT security as well. With a massive amount of data with the IoT devices, it's okay. But when we talk about the security challenge, we cannot go with only the IoT devices, or we cannot train on the IoT security. So we have to go for another technology. And for my case, blockchain serves the purpose. So blockchain is the best solution for IoT. Yes, and it is growing. Yeah. If you talk about in India, we are having many banks which is working on blockchain. Any other question?
Any other?
I got one. Thank you very much for your presentation. It was too interesting. I want to know how many blocks do you need within the blockchain methodology for to get a secure system in a company, for example?
Okay, yeah, that's a very good question. For my case, I have used 3800 sensor data. So for that, I have used only 5 blocks. So more the number of blocks, more the number of data, I mean, the blocks is going to be increased, but it's okay. For 3800 sensor value, if we talk about the hardware, we need 3800 hardwares. But if we talk about the blocks, we just need 5 blocks. Yeah. Thank you.
Okay. Anyone more? Yes, please.
Hi, thanks for
Hello.
your presentation. In this case, did you work with the MCU 8260?
Mhm.
Well, that is a very common device, but what happens when you want to try with a high level device? I don't know, more complex
Yes, yes.
hardware.
That was only the one phase of my PhD. I haven't used, I mean, only the node MCU. It's just the basic, just to check out whether it is sending data onto the blocks or not. I am using otherwise AVR PIC microcontroller for the rest of my thesis. Yes.
Thanks.
Yeah, welcome.
Okay. No more?
Thank you for the patient
Okay.
listening.
Well, then we will give her an applause. Really interesting work. Okay. Okay, then we will continue with the Dr. Sergio Vergara Limón with the title of the talk, 27th year using FPGAs on technological development. It's the is the principal organizer of this international workshop. Then, okay. His academic overview. Dr. Sergio obtained his BS degree in electronics in 1994 here in the FCE. His master degree in optoelectronics in 1997 and his PhD in optoelectronics in 2000. He has been a member of the National System of Researchers, that is SNI, here in Mexico, since 2002, and is currently holding the level 2. He has already more or less 180 international papers and a really, really great career and scientific research. And since 2005, he has been working as a full-time professor and researcher, titular A, at the Faculty of Electronic Science here in Puebla. Okay, let's give us an applause. Begins, please.
Thank you very much. So I will try to present last 27 years working with FPGAs and show the evolution of the projects that we are participating in. So this is very nice to have now a big group of people working with us, our colleagues. So 27 years ago were our students, now are our colleagues, most of them. So it's a pleasure to work with them for several years. So we have to go to United States to develop our PhD thesis in 1998, and we start working with FPGAs in two projects. First, to develop automatic systems to characterize the Fermilab pixel module and the optical readout and control interface for the BTEP project. At that moment, Fermilab has the most energetic beam around the world. Now it's in CERN, since 2007 year. So, but at that moment, this is the most powerful beam on the Earth. So the main goal of this experiment, it's called BTEP, is because they were studying the quark B. See, here are the quarks, up, down, B, charm, etc. So the atom contains electron, the nucleus, and the quarks is inside of the nucleus. They form the neutron and proton particles inside. So here we can see the quarks, up, charm, top, down, strange, and bottom. This is the main goal, study the bottom quarks. So this was the design of the spectrometer. And this is the part that was containing the pixel detectors. These little lines in red is 31 station with millions of pixels to read out. This is a schematic of the detector. These are planes with the pixels, and we can see here these planes. And we have here the fingers, it's called the finger, and we have the detectors here, the pixel detectors. So these pixel detector chips was here, and we need to read out all this data. And then we need also to characterize all these pixel chips. So we need to develop automatic system to characterize the Fermila pixel module. Consists on 5 pixel chips called XFX1, Fermila pixel chip. But the main goal was is to use commercial devices, because it's very expensive and take very long time to build electronics for this purpose. And they changed the design of the chip, and you need to develop again the electronics. So that takes longer. So to decrease the time of development, they request to do this with commercial instruments, data generators, logic analyzer, programmable power supplies, all that stuff to use to characterize the devices. So when we arrived, this took about, we made the calculation with the devices that were current in the lab. Now it's better? Okay, thank you. Then it took about 100 gigs to characterize the devices. So in 2 years, with all these devices, we changed all the equipment. And then the goal was performed in 6 hours. You inject the charge, you characterize pixels, and you took data with the logic analyzer, send the data to another computer, and process the data in real time. Then the tests take 6 hours, and a few seconds after, you have your plots, and you have the data of the characterization. So another project was to develop the readout, the PIQ data acquisition system using optical links. So we need to develop a 104 megabits per second optical link, radiation resistant, because the beam was very close to the pixel detectors. So you need to use devices that resist the radiation. So we use here a new laser at that moment. It's vertical emitting laser, a VCSEL, and a PIN photodiode. And we found that at ultra high frequency, the PIN photodiode, the new PIN photodiodes, can be used as photovoltaic mode. So like solar systems, solar panels. So you don't need to power the PIN photodiode with the external power supply. Then you reduce the noise. So the bit error detect decrease highly. So, and also we instrument 1.04 gigabits per second and use for the first time an FPGA to code and decode all the data and to handle all the data. So at that moment, the FPGAs were very new and around the world, and it's a very powerful FPGA of 2,500 gates. Only 2,500 gates, and was very powerful. No? So now, at the end, we integrate both systems to test the optical links, and you can see here the gigabit interface, the pin photodiode, the laser. So we make all the tests, and the projects were succeed, and we began working with this. After this, we were invited to participate developing the electronics of the Alice cosmic detector, cosmic ray detector called Acorde. For Alice is the part of the program of the CERN. They have CERN, the Central European Research Nuclear, and this is the location of the Alice project at point 2. The laboratory is so big that is shared by Switzerland and France. So you need to have your passport with you, because sometimes you are in France and sometimes you are in Switzerland. So this is the spectrometer, the Alice spectrometer, and Acorde was the Mexican contribution, but was the first time that Mexico contributed with electronic systems to this kind of experiment. Always they buy, the physicists buy the electronics, commercial electronics, and they instrument everything, interconnect everything, and then they work with this in the experiments. But this was the first time that we developed electronics for this experiment, this kind of experiment. So these are the modules, the Acorde modules, very big structures. This is a closer view. These are the detectors, plastic scintillator detectors that can match a photomultiplier to read out the information. So one of the problems was to characterize these devices, these detectors. So we developed automatic system to characterize the 120 plastic scintillator for the detector during 2003 and 2005. We use a DIQ PCI card that we developed. At this moment, we use an 5,000 gates FPGA, the double of the first one. We use LAN connection to program the high voltage power supply, and we perform the characterization of this is making by using cosmic ray. So the particles are coming from the space, hits the atmosphere, and produce a shower, and then pass through the plastics, muon, ray gun, and the ray gun is absorbed by the first plastic, so they don't produce heat in both plates. So when it's a muon, then crossbow, and then you have coincidence. This is what we call coincidence. Hit the both plastic and produce signal. So you can scan this as function of the distance, and you can see the efficiency of the modules. The experiment requires 98% of efficiency along the plastic scintillators. So one person could characterize this in about 1 month, one module. It's a long time, 120. So with this system, 30 minutes, one module. So we can detect errors construction failures and all that stuff. And we can take back the modules, reconstruct, redesign, and always fix the problems. And then we can characterize again the modules. This was the FPGA and the PCI card that we developed for that purpose. And this was 5,000 gates. Later, we use FPGAs to develop the electronics of the acorde. This is more complex. You need to build a header to say where the event was, which module at what time, and we need to connect to the trigger system. That is a system that synchronizes all the detectors. So all the data, the timestamp, and all that is built here in the data header generator. And later, we need to connect to the DIQ, the data acquisition system of the ALICE. So we need to interface with them using a Dorer card. And here always has a trigger card, Dorer card. We connect with both systems. And then we use 2 FPGA of 100,000. Now is 100,000 FPGA is in full 200,000 gates to develop this system. And also produce the signals that say if there is a hit or there is not event. Here is in 2006, we deliver the electronics. This is Ivan, physics and mathematics faculty here at UAP. Guy Page from UNAM, Gerardo Herrera from Simvestab, Jaime Cid, the director at that time of the faculty, Arturo Fernandez, he was a charge of acorde. He invited us to participate, Dr. Aurora Vargas. And this was Villalobos from United Kingdom. So we are in the DIQ lab at CERN, testing all the electronics before the installation. And here we are performing testing for all the detectors are connected, and we prove that the signals and all, if everything was working fine, and the detector was working perfectly, and then we make upgrade. Now we use 200,000 gates chips, and we change the cards. So we need in this kind of experiments always they say I want this and this and this and this and this and this, and this is growing all time because they need more signals, more processing, etc. This way, this is a current monitor. All this work is in high energy physics instruments. And they request a current monitor with these scales, very high accuracy. But the problem was that this is a time projection chamber. The particles cross the chamber and produce discharge. They exit the gas, and the gas produces electrons. And with high voltage, they collect with a very high speed. And this allows to turn on all the electrons, the front-end electronics, to catch these electrons, this charge. And then because this consumes so much power that you cannot turn on the electronics. A billion of channels. And then it's not possible to maintain the power of all the front electrons. So they lower the electrons and then turn on all these front electronics and they catch the event. So the problem of this detector is that use a gas electromultiplier. So this is a plane with holes, multi-layer planes. It's like printed boards in electronics. So they make holes, tiny holes, micron of diameter, and then when pass through with the gas in the detector, this produce charge, and the high voltage collect this charge. But that is aggressive, then destroy these holes with the time during the operation. So they need to measure the current of the detectors to see if the detector was working fine or was destroyed. The problem is that very little noise inside the signal destroy the functionality of the detector. So it's very sensitive, the detector. So we developed this device, installed on current monitor block. Then this is a block diagram. We have the gem. We receive the charge. We amplify. We convert from analog to digital. And then we use a high voltage isolation optocouplers. So to communicate with FPGA, so to reduce the noise from the digital part to the analog part. That was the main goal, reduce the interference, the electromagnetic interference inside the board. The current accuracy was about picoamps, and we have the three scales in microamps. So we developed another card. This was 1 million gates. Now we start 2,500 gates, and now this is 1 million gates. So we changed the FPGA, and now we have 1 million gates, and then they developed the card, very clean card. We don't use coils. And then we isolate the digital part from the analog part, and what's working perfectly. The detector works without any problem, and we reduce a lot the interference, the electromagnetic interference between digital part to the analog part, because that is the problem when you use digital and analog. Digital has very high frequencies to structure the square waveforms in digital. So the components of the frequency in the digital is very high. So it's very easy to produce electromagnetic interference. Now, in high energy physics, everything happens so fast, nanoseconds, picoseconds, and the strength is very high. So in 2005, we come with Dr. Jaime Cid, and Dr. Aurora started working here in the faculty, and we met Dr. Fernando Reyes Cortez. And then he invited us to participate in the master program to apply all this technology to robotics. Then they say, we need to close the control loop in 2.5 milliseconds. Say, okay, it's a lot, because we were working in nanoseconds, picoseconds, and the constraints are very hard in electronics. So we start developing the EQ cards. This is using PIC in 2006. Is the first FPGA card. This was thinking to develop instrumentation for use for our students in the laboratory. So we, this card, we have digital channels, analog channels, and also we developed the FPGA daughter card that we use for many projects. The PCI card, at that moment, PCI was the boss, the most used boss in the computer. And we developed a card to control 3 grade of freedom robots, and also a mini lab that has 2 channels, oscilloscope, 10 megahertz oscilloscope, 16-bit data generator, 32-bit logic analyzer, all the equipment, and also an arbitrary waveform generator. So all in one card. And this was 500,000 gates, this FPGA. Was before the 1 million gates. We changed the board later. Could you push on, may click on the video? Just a few seconds, please. So
Osciloscopio toma
the
1.
oscilloscope that we developed is very easy to use. You can see you need to move a lot of buttons in the commercial oscilloscope, and here 1 click and that's it. So this is the 10 megahertz oscilloscope. Is the video. Please, also a few seconds.
Yes.
This, here we use the card, and we put here accelerators, and you can control the rod with your own arm by wire. Here is by wire. Next, please. El siguiente, por favor.
Yes.
Okay. And here is wireless. We have the interface, and also we have the accelerators, and also a glove that sends the movement of the hand, and you can use to send commands to the robot. And here is the first, also Dr. Reyes invited us to develop a driver, a 3-phase motor driver, to have a direct control torque motor. So this is the first design. You can see it's a huge electronics, and we could control the industrial robot with our own technology. This was between 2008 and 2010, and this was the first approach. Now, okay, I lose the control. Here. And we started a lot of work with Dr. Fernando Reyes as collaborator. And here is the inverted pendulum. Also, we start to develop medical instruments like electromyograph or electrocardiograph, 24 electrocardiograph signals. And here, this is a microvolt. So, and the electrocardiogram was easier because it was malleable. So we developed all this stuff with this card. And then we need to process the digital signals inside of the FPGA. So with 1 million gates, you can use that to build your own processor. So we build our own processor, and our own language is called D language because Dr. Daniel was developing the software and called it like himself. So this is a schematic of the processor, and it's like any other processor, so there's no big deal. But we're inside and we have our own software, our own instructions. So we start to process the data inside. And it was very expensive to develop FPGA daughter cards. So like China sold these cards in 2,500 pesos. And has memory, RAM, FIFO, FPGA, Cyclone 5 with 1 million gates. So that is cheap. Only the FPGA costs 3,000 pesos. So you cannot compete with that. So we use this with one card, with the FPGA and the microprocessor, we have the computer, we have the RAM, the ROM, and all the firmware what we developed before for robotics, we include here. And then you can have all the electronics in one card. Only the power electronics is outside, and the Wi-Fi module, because we connect here wireless, Wi-Fi using a Wi-Fi module. And then you can see this is all the electronics. And we use a PC power supply to power the electronics. Here is the Wi-Fi module, and this is the card for connections, and this is the FPGA. So it's very easy now to pile all the cards. This is the power electronics, also very tiny cards, very light cards. So the system, the complete system is all this. And this is a high precision robot used for optical test. And we also start working with Dr. Jesus Lopez. He were our student and developed this robot for optical purposes to measure specters, optical specters and at UNAM and the Laboratory of Quantum Optics in UNAM, at UNAM. So him did the master thesis with us, and then he went to Polytechnic school at Mexico City and studied how to develop dynamic models. And then we start working with this. This is the software to connect with the robot. A video, if you can click on it, please. A few seconds. So, okay. And then we develop a 3D printer to learn how to develop industrial robots. That's our best interest on that. And we developed the 3D printer robot 3 Grade of Freedom. You can click. It's in high-speed video. And then we found that the printer were more or less okay. But if you can see, this is round. The coordinate is not in 90 degrees. So we can see here any change of direction is rounded. So that is not correct. Then we start to develop the techniques to make better accuracy of the robot. And we found that this problem is because the friction. And then we start studying friction And we can see 9 millimeters without friction compensation at the beginning of the performance of the robot. And later, we reduce this at 5 millimeters, 1 millimeter, 960 millimeters, and then 50 microns because friction. So it's amazing how changing introducing the dynamic model to produce trajectory control and compensate the friction with all the phenomena, you get high precision robots. About 2 mils is what the industry handled in the industrial models. 1 mil is very high precision, 2 mils is commercial precision. So for x-axis, we have 27.5 microns. So changing the compensation of the friction and implementing the trajectory control. So with then we can see now the corners are 90 degrees. This is 2 traces, and the robot pass over the first line without any triangle. You can click on the video. ¿Podrías poner clic en el video? And now the corners are now in very good shape. They are not anymore rounded. This is 3 T-traces. And this is 2 traces. If you can click on the video, please. Okay. And also with this robot, we implement a scanner. We put a tip here. And we develop this tip because the sensors are very difficult to push and destroy the surface of the test. So we develop our own tip to scan. But what we want to do here is we have a very high accuracy with the robot running. But what happens if the robot is here and moves here and stop? The friction is a problem. It's not the same problem. If you are running freely, the motor is running, the friction is reducing, no problem. But when you say I want to scan some surface, 3D surface, and you say I am here and I want to move 100 microns steps, then there is a problem because you stop every time you are stopping the robot. And then we can see here the static in plot torque with speed versus speed. You can see here how the friction doesn't allow to the robot to move. Then we compensate that, and we have almost direct transmission robot, almost a linear. So what you want is a line that cross zero. And then you say to the robot, move a little, I want this torque, and then you have. That is what we produce this kind of response. Also, we can see the phenomenon here in the y-axis, and here is compensated. But this is very difficult to do manually. So this is a work that developed Juan Pintor. See, he is helping us now with the Congress, my right hand. Then he manually took about 2 months to calculate, and with experimental error, there in a loop, they measure, they calibrate, and all that stuff. It took about 2 months to do each axis and get a very good results. It's about 100 micron step, and we have plus minus 9.2 microns, so about 10% of error. And also he could achieve 10 micron step, but he doesn't report, it was too much. And this is the Y resolution, and we can see the same, about 10% of error. But we are talking about 100 microns, and the road is stopping each step to scan a figure. Here is a video. If you click, you can see here the step and see how to move this just a little every step. Look at that tiny movement, and we have a lot of reduction in movement, so it's very precise, and it's a closed loop control, closed loop. So we scan this figure to see how we scan this, and you can see this scratches. This scratch was made for accident, but we use to see if the scanner can see this. If the tip can measure this, and you can see the plot, and here we can see the scratch, but amplify it, we can see this big scratch, this and this, and you can see here in the plots, we can see that the scratches in data. So it was not me. It's not my fault. To end, it took too long to, thank you. Took too long to calibrate this friction and all that stuff. So Dr. David Pinto invited us to participate in a PhD program. And but was on computer. So we say, what we can do, we do instrumentation for robotics, and now you want to change now to computing is a big deal. But we see opportunity to develop application with artificial intelligence. And we apply the convolutional neural network to make the parametric identification for robots. So we have now the dynamic model, but we don't have the parameters. We need the parameters. So we use artificial intelligence to know these parameters. Yes, I am finishing. Thank you. So we can convert signals, electrical signals, into values and produce image. So this image you can use to work with the convolutional neural networks. So we mix all this knowledge, and we start to produce with the dynamic model the base of data. So now you have you can produce 500,000 simulation and get 500,000 image, and then you can train your CNN, and you can use that to provide real information. So your experiment, you measure position, torque, all that variables, and then you produce image, and then you put inside of this, you process with the convolutional neural networks. And then what happened? That you get your parameters, experimental parameters, real parameters. And what happened? This is the simulation and the experimental results. Position with versus time, velocity or speed versus time, acceleration versus time, and torque versus time are the same. 98% of coincidence between simulation and reality. So in simulation, you reproduce the reality without robot. Now with this parametric identification. For both axes, these are the results. And then we have now working a lot of PhD students doing that for every robot that we have. Okay, this is the historical production, the historical academic production of the group, about 990 GCR indexed papers, 45 master graduate students, 8 PhD graduate students. We start with PhD students, working with them since we have 7 years ago. So we have not long in this. 6 master students with thesis in progress, a PhD student with thesis in progress, plus 4 for the next period, 10 patent granted, and 4 patent pending. And that's all. Thank you very much.
Thank you for your presentation. Anyone have questions? A little, because
I hear someone, but
question? No? Okay.
yes. Sorry, I can't hear you.
Yeah, my question is, when is the correct time to use Alice experiments on CERN?
A ver, mejor en español, si quieres decirlo.
Sí,
Pero sí.
había mencionado que no se pueden usar siempre o hay un área específico para utilizar los experimentos de Alice en el CERN. No sé cuándo en el año se puede usar, porque el consumo de energía había mencionado que era demasiado.
Okay. His question about the TPC, how is the cost of energy? The front-end electronics for the TPC, it's about 1 times 10 to the 8 watts. It's huge. And then that's why you don't want to take all the energy and leave the people freezing during the winter in Switzerland or France. So that's why they need to turn off. They sense a heat. That's why is, for example, the Acorde detector. You have a heat, an event, and then you turn on the electronics and then you capture the charge. Because it's huge, it's about times to 8 or 9 watts.
Y bueno, el consumo que se produce, ¿quién lo paga? ¿La Unión Europea? Porque, bueno, la energía cuesta, ¿no?
The CERN is the money comes from many countries, including Mexico. If you have projects here, you have a granted projects, financial projects with CONACYT, and you put the money on CERN accounts. So all that we developed was paid by the country, by Mexico. The benefits are huge because you have a lot of technology developments. Actually, I don't know if you know, that internet was developed by CERN. Like people like me, you have your salary from your university, and they invite you, develop the internet. And you join with some colleagues, most of them your friends, because you work for decades together. So they develop the internet and finish the work and leave it. They go to work on another project. That's why nobody claims the paternity of the internet and charge you to connect the internet. Total Play, Infinitum charge you to make the connection. But when you work in your browser looking for something, nobody charge you. It's because of that.
Gracias.
Also, your players, the MP3 players, are software that compact data because these projects produce a huge of data. The quantity you can imagine. I don't imagine so much data. So they doesn't have where to storage that data and build something new all time, and the technology is developments are very many. Nothing exists. When they invite you to produce something, it's because doesn't exist the electronics or the software to compact the data. Anyone? Okay.
So you have, you made many protocols and many boards. Do you receive any funding from Mexico government or maybe the university here?
No, we have a little bit projects. All this has built with projects about 20,000 per year pesos.
And you're
The
spending-
funding from CONACYT is very difficult. If the physicists request money to buy devices, like some of them ask me to recommend some oscilloscope,
Oh,
4 gigahertz oscilloscope, $50,000. In Mexico, $75,000. And they approve to them.
okay.
You don't use them, don't use the device, but they approve to buy the device to them. But if we apply, they say, no, why you don't, you want that kind of device? So it's very difficult to get funding in Mexico. So this is more the contribution of the students, like Daniel, Carlos, Juan, Michelle, that works every day implementing all these ideas, but it's because the students. And also we're going to show that everything is, in Mexico, there is a problem. Everybody says there is no money, but they have money, but doesn't develop anything. And we have no money, but we can develop all these things. The mechanics is very cheap because we design and build everything. In every robot, each robot it costs commercially thousands of pesos, but we have here very cheap. This robot has 10 years development, this printer and the scanner, and the investment is very little. It's about 50,000 pesos during these 10 years. So that is the funding.
And for patents also you need to pay. There is a fee for patents, applying for patent and filing and maybe grant. Are you spending any money on patents? Like you have patents, right?
Sorry, I don't hear very well.
You're having many patents as well. Patents. Yeah. So are you spending? Oh, okay. Okay. University is spending.
Yes.
Okay.
That's why these patents are we are the authors of the patent.
Oh,
The owner is the university.
oh, okay, okay.
But we register the software.
All right.
Actually, all the development software, Daniel, are copyright
Okay,
register, and the patents, and also the articles, the papers.
okay.
So we try to protect everything because
Yes,
anyone can come and
yeah,
tweet.
sure.
Actually, it's happening in Mexico. The Virgen of Guadalupe, do you know about that? Is has a huge temple in the Mexico
Yeah,
City.
I know. I
Oh,
just forgot the name,
okay,
yeah.
the stamp of this
Yes.
Virgen of Guadalupe was not copyright.
Oh,
They came Chinese people, and they register.
oh, yes.
Also, Hecho en Mexico, the old logo of Made in Mexico, they register. And no one can use now because you need to pay rights.
Yes.
No, the government, Mexican government developed the second Made in Mexico logo, and now it's free, but I think that they register now on copyright.
Same thing happens with Indians also. We just filed our patents, but after 1 year, we see the product in the market and made up of China. We see the same.
Actually, CERN learned the lesson because lost a lot of things,
Yeah.
a lot of the technological development, software, hardware,
Yes,
firmware.
yes.
And they now are patent and register copyright
Yeah.
so in
Yeah.
software because Steve Jobs, for example, wants his music in one little device,
Yes.
so he can run
Yeah.
every morning with listening to his music.
Yes.
And then at CERN, they developed the MP compact software. And they took, the company took the software and used to produce MP3, MPGA, MP4, all that movies, compressed movies, audio, music, data. And then nobody charged them because it was for free.
Yes. Thank you.
Thank you. A little break, coffee break. Then we will return 10:20, please. Okay. We need to continue because if not, we are taking time of Dr. Carlos. Okay. Well, we will continue with the presentation. And now is the time for Dr. Carlos Leopoldo Carreón Díaz de León. The title of the presentation is Internet-Based Socket Automation for PM/ISM Control. I will give the academic overview of the doctor. Dr. Carlos Leopoldo Carreón Díaz de León is a full-time associate research professor at the BUAP Faculty of Computing Science. He holds a PhD in Language and Knowledge Engineering, a master's degree in Electronic Science with a specialization in automation from BUAP, and a degree in Mechatronics Engineering for the University of Veracruz. His research focused on the parametric identification of manipulation robots using convolutional neural networks. He has participated in research studies, direct degree thesis, developed registered software, and published scientific articles in indexed journals such as IEEE Access. He teaches courses related to programming, networks, operating systems, logic, physics, and cybersecurity. He also collaborates in updating the information technology engineering curriculum at BUAP. Okay, please give us applause. And begins, please.
Yes, good morning. My name is Carlos, and today I want to talk about an internet-based socket automation for a permanent magnet synchronous motor control. My name is Carlos, and I'm from the computation faculty. If you want to talk with me, this is the place that I work. Okay. Here we have the content of this presentation. I'm going to give you a brief introduction about the topic. And then we are going to discuss some basic concepts related to the web technologies, also the permanent magnet synchronous motor, basic theory. Then I'm going to explain you PNS automation architecture, in other words, how to connect several computers, yes, to handle the motor and provide the motion. Part 3 contains several results that we obtained using this beautiful platform, just for me. And finally, we have the conclusions and the future work and the contact if you want to talk with me, okay? We have the introduction. WebSockets and application programming interfaces, APIs, enable the real-time control of systems, such as a permanent magnet synchronous motor, PNSM over the internet, facilitating smart automation in industrial environments, and enhancing the capabilities of connected robotics through efficient and responsive communication. So in this figure, we have several machines. In that case, we have three permanent magnet synchronous motor. We have a robot, and all these machines would be connected to a server to be handled by the internet. This is an amazing technology because you don't need to have the machine in front of you. You can drive it by the internet. Yes. We have some basic concepts, how the internet works. The internet works by connecting local area networks to wide area networks, allowing devices in different locations to communicate with each other and enable systems like remote automation of motors and robots. In this figure, we can see a schematic diagram of how the internet works. We have several devices. Please remember, the internet is multiple devices connected between them and transfer data for example, position data. Yes. For example, the system that you use to view your qualification. Yes. We have what is a server? It's a machine, it's a computer, it's a robot. I don't know. A server is a computer that receives and processes requests from other devices, acting as the core of remote control and automation system. In other words, a server is a computer with enhanced features to handle multiple requests. Yes. For example, in this work, I use my personal computer. It's a World One personal computer from 2016. Yes. And this computer serves as a server, yes, to provide the motion of the permanent magnet synchronous motor. Okay. We have the internet protocols. When you communicate in the internet, you need to use several protocols to establish a good manner of communication between the machines. In that case, in this work, we use HTTPS or Hypertext Transfer Protocol. In other words, how to transfer data between a server. And when you open the navigator, you view, yes, the website. This is HTTPS. And also we use WebSocket WSS protocol. The main difference between these two protocols is that the WebSocket maintains open the communication between the machines. For example, a client that open a website and the server, the connection is open. It's like when you transmit a video, yes, the connection could not be closed because it produces several time delays. So we use this protocol. Okay, a protocol is a set of rules for network communication. HTTPS enables secure exchange while WSS maintains a real-time connection for a system like remote motor control. Another important point is that my computer has small filters. That means that it's not possible to transfer a lot of data because it collapses. Okay? We have 1.4 JSON format, back-end, front-end, API concept. The front-end displays the interface that the user see. The back-end process the logic, and both communicate through APIs that change structure data in JSON. When you open a website, the first thing that you see is the elements in the website. For example, in this time, I have a control in my device. This is called the front end, the part that the client see. However, in the back end, this is all the logic necessary to create your website, for example, dynamics, your interaction with the buttons, okay? So we have two sides, the front end and the back end. To make the communications more efficient between them, we use a format called JavaScript, yes, that packages the data and transfer between these two parts, the front end and the back end. Okay, so we have the permanent magnet synchronous motor, basic theory. In this case, we have several coils, as we can see in this figure, yes? Each coil generates a magnetic field that the main purpose of this motor is to synchronize it with the rotor position. So we have usually three phases in that motor, and we have the equations. In this case, the equations usually are given in ABC frame. For example, the electricity that CPA gives us could be delivered in three phases. And yes, we have the motor. This is the permanent magnet synchronous motor, and obtained from a scooter. Okay, we have another equation. So in this work, we need to translate our ABC frame to another frame that is called DQ frame. In that case, the DQ frame moves together with the rotor of the permanent magnet synchronous motor, and it facilitates the equations, because as we can see here, we have the torque. Do you remember what is the expression of the torque in a direct current machine? Anyone? No? Well, in this machine, the torque is given by a constant multiplied by the current. So in that case, we have a similar expression. We have the currents that we visualize in the DQ frame, and we have this special multiplication, and we obtain the torque. A very important point in this work, I don't implement a direct current control. I'm just apply a voltage control to move the motor, and well, to implement this application. Okay, we have the permanent magnet synchronous motor automation architecture. Yes, we have this architecture. I'm use a Cloudflare proxy server that protects my computer from external attacks. Yes, the internet is plagued is a lot of automated bots that try to hacker the computer and try to make the system to work, for example, mining Bitcoins. Yes. So this is a very important block, the proxy server, and we have the clients. You can use your computer, your device. I don't test it on the watts, but I believe that it's possible. If you can access with your watts to the internet, it's possible to manipulate the permanent magnet synchronous motor. So this is the internet site, okay? And then the proxy server knows my public IP. In that case, this part says private server address. In other words, the location, the real location. So this proxy server, this Cloudflare server does protects my IP, and then the data is transferred to a router. A router connects the main server that, remember, is a personal computer with small filters, yes. And I connected to the DE1 COC board, and then the firmware generates PWM signals to handle an electronic driver, and that moves the permanent magnet synchronous mode. This is the main idea, that when you access to my website, you can manipulate the position, you can manipulate the gain, the constant gains. In this case, we use a proportional control without any kind of derivative action. Yes, moving on. We have a main server architecture. Yes, in that case, we use a Python language with a framework called Flask. It's a micro framework because this dependency allows to implement the web server. So in that case, we use three threads in the main server. We have the web server, the queue status, and request API data FIFO. So we have the front end and the back end. But please remember, the front end is protected by the proxy of Cloudflare, okay? So we transfer the parameters. In that case, these parameters are the desired position, proportional gain, and in that work, we use a hyperbolic tangent. So we have a constant that manipulates the argument of this control. So we use a format. Please remember that the JSON format is a special way to package data. It's, for example, when you send a package from FedEx, yes, you put in a box, you put several things, your name, I don't know. In that case, JSON is a special packing data. Is to use it in web technologies. So we use the HTTPS protocol, Hypertext Transfer Protocol, with secure. That means that these data transfers are not allowed to view to other people. Just for example, if you talk with your partner about your password, just for example, in that place, if you screen your password, well, it's not possible to protect you because you are telling all the people your password. However, if we cipher the data, this is not possible to view to another people that is not involved in the main conversation. Okay? So we have this thread, the web server, that render the template, in this case, put in your device, yes, the website. Okay? So when the permanent magnet synchronous motor moves, We obtain the result as the same way using JSON data. Yes, inside the main server, we have another thread, the queue status. This thread tells us the connected clients, the status of the permanent magnet synchronous motor. For example, when you move the motor, when you control, you can view how many people or how many requests are there. And yes, it's possible to view when is your turn to use the motor. Yes. It's very important that this thread, the queue status, use WSS or the WebSocket. That remember, the WebSocket doesn't close the connection, maintains alive, so the communication will be remain until you close your device. Okay, so we have another thread. Thread in that case is called request API data FIFO. So we have in this thread all the requests made by all the clients. So it's put on a special list with an user identification, yes, and we use global variables. In that case, we use it in asynchronous mode. That means that it's not necessary to stop the entire process to consult the global variable. So we have the status and send to the queue status thread, and also we communicate, yes, with the web server. Why? Because when a client make a request, it is put in this FIFO, yes, and the result is obtained in a synchronous way. Yes, that is my form to implement. Maybe there is another more efficient way, I don't know. Okay, we have the web server. In that case, all starts when you press start experiment. We called this URL, and then we call the API with a post method. When you access through the internet, it's possible to access with several methods. For example, you put google.com in your navigator, you access through a get method, obtain, get. However, when we use the post method, we are going to put data in the website. So we send the parameter data with JSON format, then we create the user identification, append to the request in the queue. Then we ask if the user ID is in result. If not, we await for 0.1 seconds. If the user ID is in the results, we delete the results from that specific user because it's sent to the client. And finally, return the results and end the experiment. Yes? We have the queue status. All begins when this connection, and this connection is very important because it's when the server establishes an alive communication with a client. So the server sends the socket.io, is a dependency, is it in JavaScript, to the client and establish a socket connection. But please remember, this connection will not be closed. It maintains alive until you close your website. Okay, so we make a variable called status, and we include the number of requests, the API status, and the list. So in the website, we are going to view the queue and how many people request the permanent magnet motor synchronous, the permanent magnet synchronous motor to move. Okay, and then we send this data through the WSS protocol. Remember, it's an alive connection. Okay, we have the request API data FIFO. We start this thread, and this thread doesn't stop until the server, the main server, is closed. So maintains executing, yes. And first we get the parameters from the queue FIFO if there is a request. If the queue is empty, this algorithm stops here because you don't have a request. So it stops until a new request is stored in the FIFO. Then we put the status variable to true. We set true, and request a result from the API with the given parameters. it's very important to note that this address is a local area network address. That's because the main architecture, yes, connects the board and the main server through the router, but doesn't expose the DE1 board to the internet because it's a very, very insecure practice. Okay, so we take the data. We await if the API sends a valid response. Yes, if we have a valid response, we append the user ID to the response and then return it. If not, we await until the API response contains the user identification. What does it even mean? That you need to wait until the API solves your request to move the motor. We have hardware and API connections. So we have in this part the main server backend that it's connected through the request API data FIFO thread and sends the parameters. In this case, please remember the parameters are the desired position, the voltage input, the saturation gains, and the time of experiment. So we send to another thread, but in that case, we use the embedded board with an ARM processor and FPGA. So we send the data, and then it is processed, the control motion, by a function called PNSM control function. So this function interacts with these firmware blocks that generate the three-phase signals to a three-phase MOSFET bridge. And also, we can read the sensor of the motor. In that case, we use an encoder that needs to be read through that way. Okay, so we have the web server, but in that case, embedded in the board, the DE1 sock. So when the main server makes a request using this URL, remember this is a local area network address with this specified port. We read the parameters with JSON format. Then it is very important to block the permanent magnet motor, because if we don't block, it is possible that multiple people try to manipulate the device without any kind of control. And the board has not huge filters to support this kind of experiment. Then apply the JSON to the output results. In that case, the output results is the position, the velocity, acceleration, and the acceleration not, I don't put it. Then release the PMSM and finish the experiment. So we have the function control. In this case, we read the voltage of the sensor. In that case, the encoder, the current sensor. Yes, these equations need to be implemented because the encoder that I made has several distortions in its shape. Yes, because it's a piece of paper, a round piece of paper that has several deformations through the angle. So it's necessary to modify in some way the signals of that encoder, well, to be able to calculate the position. Yes, I know maybe a commercial encoder will be an excellent option. However, I made it because I want to experiment with this very cheap encoder. I mean, just 1 peso. Okay, so we calculate the position. Then we apply the, we calculate the torque with the Clark-Park transformation. In that case, we don't use a direct control torque, just we control the voltage. So this is for client information. And this is the voltage control. We use an hyperbolic tangent that is multiplied by the Ks constant or saturation constant, multiplied by the desired position minus the actual data of the motor. And then we adjust to have in this range, 0 to 1023. Okay? So we have the electronic diagrams of the H bridge. It's important to notice that we have the same thing of MOSFET transistor. So in that case, we use a pump, a voltage pump that multiplies by 2 the input voltage to obtain a 24 volts and then be able to activate this part of the H bridge. So this is a technology that we implement, and it's amazing because this transistor doesn't get hot. Okay. Moving on, this is a picture. Yes, very nice. This is the encoder. We have the sensors. The CNY17 is used to read this pattern that is put in the rotor. So this is the encoder that is mounted in the motor to estimate the position. And we have the results. Sorry, interfaz en español, interface, sorry. Please open your phone and scan this QR code, and you'll be able to handle the permanent magnet synchronous motor with your phone. So the first part of the website is this logo. We have internet basic socket automation of a permanent magnet synchronous motor control. If you click here, you can find the presentation, this presentation website. Okay, moving on. So we have several controls. In that case, we have the voltage input that you can see as a proportional gain. Yes, proportional gain, saturation gain. We also can configure the desired position. I'm sorry if the server stops working. Yes, I'm not tested with a lot of people, but well, and we have the parameters sliders to manipulate the PNS motor through the internet. So, okay, so you can handle the motor, okay? Yes, these sliders are in gray color because they not used in this work. So this is an example of a queue. We have several requests, okay, several requests. We have a busy button that tell us the status of the permanent magnet synchronous motor. So we have several signals, in that case, the position. It's amazing how a basic voltage control can turn the motor to 1 radian. Okay, so when direct current control is implemented, it can improve more this result. Also, we have the velocity. In that case, the velocity have these variations due to the deformation of the encoder. Please remember it's a piece of paper, okay? We also can,
You have only 5 minutes left.
yes, thank you. We can also control, sorry, we can also know the Fourier transform of each signal, the position, velocity, encoders, the current. We have the encoder signals. Yes, in a future work, it will be improved to put in the same way, the same magnitude. Also, we have the three-phase currents and the fixed frame currents. Finally, we have the voltage and the torque calculation. Okay, so we have the expression of the torque. We need to know the inductance of this motor. In that case, I don't know these values, so I put some values. However, it is necessary to implement a parameter identification to know the exact values and improve the signal, just because the purple one is a torque generation. Okay, conclusions and future work. Well, this presentation show us that it's possible to connect machines through the internet and manipulate them using your device. And believe me, it's a very, very, very comfortable way to work because you can have your phone, you manipulate the gains without handle your computer. So it's a very easy way. You have the machine, you put your device, adjust the control, and that's it. The future work is improve the encoder, and we'll implement another motor to construct, for example, a robot arm. So there is my contact if you want to talk with me. It's my personal email. Well, the institutional email, so you can find me. And thank you very much.
Okay, thank you. Do you have any question? Questions? Yes.
Hi, morning. Thanks for your presentation. Such interesting. Let me tell you my question is what could be a useful application, for example, in the industry of these protocols?
The industrial application of that specific protocols.
Yes.
Okay, just imagine that you have several robots implemented in your industry. So it's very important to use a secure certificate between the communication, because believe me, there is a lot of people that try to steal your data, try to manipulate your robots without your permission. So these protocols protects the machines, because if we use just HTTP, it's a very, very bad idea. In fact, the last week, just I just have 23 seconds to avoid an attack. Yes, for just 23 seconds, I avoid the destruction of that server. Yes, it's amazing. So it's very important to use a certificate you can buy because they protect your money.
Okay, thank you. And another question that comes to my mind right now is how many requests you can handle with the server?
Okay, good one question. By the moment, the server is programmed to handle just 10 requests because it's a small computer, has small filters. However, if we improve this machine, maybe we can handle thousands of requests. And also we need to improve the communication of the internet to obtain a very fast response, because in that moment, I don't know if the server is collapsed. I think no, because we can still see the presentation. Okay.
Okay, thank you.
Yes.
Okay. Another question?
Thank you for the exposition. My question is, do you consider the electromagnetic interference in the industry for the server? And why do you choose the MOSFET grid for the control?
Okay, excellent question. The electromagnetic interference in industry is too high. So I believe that maybe it's an investigation topic, because yes, right now this work is working in my home, yes, but we need to improve. We need to improve it to avoid this kind of noise, because you're right. If we handle a very huge permanent magnet synchronous motor, the interference will be very high. So it's a very good question. In that moment, we use multiple earth connections to the board. The board has board earth connection to the ground, so I use all of them. Connect all this ground connection in my power supply to the physical floor to avoid this kind of electromagnetic noise. And why I use MOSFET is the other question. Yes, I use MOSFET because the low resistance of that device prevents the heat generation. So in that application, due to the motor is a small machine, it's just a scooter motor. They don't need to have a huge power demand. So with the devices, in this case, the MOSFET device that I use, the low resistance is better than I use a AGT transistor. Yes,
Okay, we will give
thank you.
an applause. Recognitions. And, okay, and all the ports. Okay. Thank you, Dr. Carlos. Okay, the next talk is by Dr. Luis Ernesto Valencia Segura with the title Implementation of Convolutional Neural Network for Solving the Spherical Mechanism Synthesis Problem and its Comparison with Evolutionary Algorithms. Okay, the academic overview of the Dr. Luis Ernesto is a Mexican engineering and researcher specialized in robotic and mechatronic systems. He earned his bachelor degree in electronics and his master degree in electronic science with emphasis on automation from the Benemérita Universidad Autónoma de Puebla in 2015 and 2016, respectively. Later, he obtained a PhD in robotic and mechatronic system engineering for the Interdisciplinary Professor Unit in Engineering and Advanced Technology, UPITA, of the National Polytechnic Institute, IPN, in 2022. Since 2024, he has been working as a professor at the Faculty of Computer Science of WAP, where he combines teaching with research activities, also serves as tutor. In addition, he is undertaking a postdoctoral fellowship at the Faculty of Biology, System and Technologic Innovation, FASBIT, in the University of Oaxaca. His research focus on the design and implementation of bio-inspired meta-heuristic for optimization and their application to engineering problems, as well as robotic model identification and signal processing in robotics. Dr. Segura stands out for this strong interdisciplinary background and his commitment to technological innovation in academic and scientific fields. Okay, please begin your talk.
Thanks. Hi, everyone. My name is Luis Ernesto Valencia. Now I'm gonna show my research. It's implementation of a conventional neural network for solving the spherical mechanism synthesis problem and its comparison with evolution algorithm. So we need the mechanism in every place, from industry to medical, and the requirements about mechanisms right now it's more high. So we need explore more efficient ways to find or design mechanisms or robots. So what's the problem? The problem is the dimensional synthesis presents several changes. So as fact that the number of the degrees of the freedom and the complex of the mechanism increment. So this make us impossible to find solutions that that we can find between through the algebraic methods. So we can think about the use it methods alternative like approach to directional synthesis using heuristic optimization algorithms among the different evolution, or in this case, convolution network, neural networks. So we have two epochs. The first present the advantage like AC implementation tends to be robust. AC2, what is the disadvantage of differential evolution? It's possible we need propose an optimal problem. We solve one problem at the time, and tends to find into the two local optima. So that is a problem because we need make runs about for the algorithms many times to try find a good solution, or make change at the algorithm. For the place, we work with convolution neural networks, and this present last advantage, the generalizations ability. You don't need to be an expert to solve the problem, but what is the disadvantage? Database with sufficient elements is required. Database, so they must be very big. And tracking can be expensive, talking about computer time. We need careful preparation the data, because we ingress data for root or that not resolve our problem, the work don't help us. Finally, we need to adjust the hyperparameters. And so, what is the aim of this investigation? While different evolution can be explored, the search space exhaustively, CNN can learn complex patterns and adapt to scenarios with significant variability. And comparison between EDS approach and CNS approach is the principal objective of this work. And maybe we can make an hybridation to find better solutions. What is the method? In this case, we propose a trajectory. If this trajectory take 33 precision points uniformly distributed with respect to the rotation of the input link about our mechanism. The metric to compare among twice methodologies is the similarity metric. We select a mechanism randomly to make this work. First, I'm gonna explain how cinematic calculate the cinematic about the mechanism. First, we consider a mechanism of four bars or links. Suppose all the bars move over an superficie of a sphere, where we have a fixed firm x, y, z, and the 0 is the center of the sphere. The input link is R2, is defined, it is defined by the points A0 and F. So the link R4 is defined for units revolution that is S and B0. R3 is the link couple. This is the R2 with R4. Finally, the fixed link is R1, is fixed link or ground. The trajectory that describe these mechanisms is we taking in the point P0. So to calculate the arc or geodesic of links, use the equation 1 to 4. To calculate the cinematic, we make it through an algorithm. Well, the first step is calculate the rotation, the R2 around the vector between F and 0. So we rotate this link, the theta graph or theta radians. This is described with the equation 5. Next, we find Bj prime. This is 5 B0 when translated to Bj prime. With that, find the position, the medium position for finally find the position Bj. That means when I know this point, I can rotate again, but in this case, what I'm gonna rotate about this point. Then I take this point and rotate to Bj. That get one problem. We need rotate alpha grade, but we need force this distance from here to here be equal to this distance. With that, we need, with this equation, we can manipulate it to get the equation 9. To solve the equation 9, get the equation 10, and get out two solutions. To get the solution correct, usamos this algorithm. This algorithm only tells us that the smallest alpha is we take it. Finally, the position, the coupling point, can be calculated through equation on 11 and 12. These equations are the same, the Vj prime and Vj, because this point is coupled to a link tree. When we have, or when we can calculate the cinematics, we can propose the algorithm. The algorithm or the first approach is the Federation evolution approach. This algorithm is easy to implement. This is based in the evolution of the species, and this algorithm begins with an initial population, and where this population have many members, where every one member is a possible solution of the mechanisms. So these mechanisms, these solutions can be mescled with another members to generate a vector like that. This vector is crossed with a member of the popular original and create a child. This child competes with the father to know who gonna pass to the next generation. This form, all members about the first generation draws the first to the second generation. That about step by step the generation draw. We can find good solutions for a problem. But we need propose an optimization problem. This is a form like we formally propose a problem of optimization problem, where we need a function fitness J, and we need find an X to minimize J. And this function is just to J and H and that are restrictions of the problem optimization. So we propose the objective function like equation 13. This equation tell us that we have Qj, and these Qj are the 33 points decided, and Pj are the points calculated about for the algorithm to cinematics of mechanism experiment. Where x is equal to the coordinates every single point of our mechanisms. The constraints are 14 to 16. And the first tell us that we need solutions, real solutions. If that equation is greater than 0, the solution is complex. So we need solution real. G2 is the solution is the restriction that about the mechanism can move. And finally, the 16 is a solution, is a restriction that helps to algorithm to make the point of the mechanism it's close to the point they said. Now, because the algorithm is thinking to resolve problems without restriction, we need introduce 100 constriction. We use the depth criterion, and this tells us that any effectively solution is preferred to inflexible ones. Between two flexible solutions, the one with the best objective function is preferred. Between those inflexible solutions, the one with the smaller distance between violet constraint is preferred. So where the distance constraint is give us by 17. That is the algorithm. That is the algorithm, and with that we can resolve the problem of with that we have the problem of optimization. Now, the second approach is convolution neural network. These networks have an input image, convolutional layers, pooling layers, activation functions, and finally, un full connector layer to get solutions about a problem. So this is the architecture that we propose. We use 5 layers convolutional and just one max pooling layer and 5 layer full connected. That is the resume about the characteristic about the layers. So we increased with input imagine the 10,000 times 10,000 pixels. We have the layer 1 and 5 are convolutional layers. The layer 6 is a pooling layer. The activation function is the function rel. This is the table, how is configured the convolution layers. So, to process data, we need generate the data set. This, we thinking this form. First, we have a trajectory decided, and we get 33 points. This point, we can separately about X, Y, and Z, this form. And posteriorly, we take just one, the three graphics, and convert in just one, where this is X, this is the part of Y, and this is C. So when we have this image, we can represent with this vector. When or where what Q1 X to 1 Q33 are the 33 coordinates X from every one point. So the imagine is create this form. First, take this the vector and normalize it with 80. Second, use the equation 90 and 20 to make the image. With that, we get this imaging, and this imaging have all information of the 33 points. With that, we can sort the convolution network, and we propose this fitness function to calculate with backpropagation the where is how the fitness is advanced. So the results. We use the algorithm invariant ED-RAD1bin. We use CR equal 0.91 and F equal to 0.3 to 0.9. And we use population number to 200 and number of generation at the 5,000, and we need run the algorithm 33 times. 30 times, sorry. So we obtain these variables, and this is the result of the algorithm. We can see up down. We can take the average was 1.9, and the best solution is the worst solution can see here. This is the mechanism finding or found. And we, at the left, have a graphic that represents how the best individual from every generation was downloaded. And this is the solution that was get the evolution differential. The CNN result with entrainment, the CNN was entrained with the backpropagation algorithm. We use length factor 0.003. We use a million epochs. And the database was have 1 million of images. The data was split in two. One to training, and second to validation of the training. If we can see two graphics of training. The first, we use it image clear, but the algorithm tends to memorize. This is the training, and this is how the algorithm, this is the validation. The second, we have to take some image and we sometimes some image we ingress perturbations that was with the objective that the convolution network, the CNN, learn inside memories. So
5 minutes left. 5 minutes left.
¿Puedo pasar? The cumulation, the CNN to get come back the data or the design variables, we use this algorithm. In this algorithm, we normalize the data or the result, and we obtain this result. With that, we obtain these mechanisms. To compare the results, we use the similarity. This is the algorithm about similarity. And this have the advantage, the comparison is in time and frequency. So we can see if how are the similar how similitude have the result of the ED the CNN. We can see the ED is 019979, CNN have a similarity to 9871. So in this case, the ED is better. Here you can see the trajectories of the comparison of the trajectories. We can see the dotted line is the CNN solution, while solid line is ED solution. The asterisks are the points they share. So we can see the ED is closer that CNN. Here we the same, but by coordinate. Here we the result of the CNN, and here have a table with comparative results. So criterion optimization is the thin optimal solution from scratch. CNN requires label data and data for training. Flexibly managed multiple objects, while CNN limited to partners learning from existing data. Computational is costly is iteration, but can be parallelism. CNN expensive to try, but fast to infer. New solution, explore innovation solutions, precision, well, high if the parameters are adjusted correctly, and CNN depends on the quality and that. Conclusions. There is more suitable for dimensional synthesis, while CNN is another approach for this problem. So, for future work, we are thinking about the, obviously for the dimension synthesis for bar spherical mechanism, differential evolutionary algorithms are superior to the direct optimization capacity. While CNN are not suitable unless a large data set of pre-optimized solution is added. If an innovative approach is decided, a combination of the reinforcement learning más DE could be explored, pero DE remains the standard in the literature. Referencias. Thanks, thanks to my support people y my contact.
Thank you very much. We have time for only one question.
Hi, thank you for your presentation. And my question is why you use ReLU function like activation function, and you think improve the trajectory of CNN using another activation function?
Yes, we can use another function inside the ReLU, but ReLU have a good desempeño, perdón. So we can use it like first time. We need make more experimentation to maybe the CNN enforcement to find better solutions.
Thank you. We give you an applause. Se van a sacar la foto del recuerdo. Okay, la evidencia. Okay, our next talk is given by Dr. Germán Ardul Muñoz Hernández. The title is Fractional Order Controller Applied to an AC Matrix Converter Driving a PM-IS-M Model. I will give you an academic overview of the Dr. Germán. He's a senior member EAAA, received the BS degree in electronic engineering from Veracruz Institute of Technology in 1985. The MS degree in electronic system from the National Institute of Astrophysics, Optics and Electronics in 1990. And the PhD degree from the University of Wales Bangor in 2005. He has with FAPAEUX Tuxtepec, Mexico from 1986 to 1987 and from 90 to 93. He has been a visiting engineering with South Carolina, Columbia, USA in 1995, Michigan, Ann Arbor, USA in 1996, the CERN, Geneva, Switzerland in 2007 and 2009, and UPC, Terrassa, Spain in 2023. Currently, he's a professor at the Benemérita Universidad Autónoma de Puebla, here in the Faculty of Electronics. His research interests include control system, application, and automation. He is a member of the National System of Researchers in Mexico. Okay, please.
Thank
begin.
you, Aurora, for your presentation. First of all, let me thank you to all the organizing committee for this invitation, and to the student, because without you, none of these events can be possible. Thank you very much. This chat is going to be about this. First, we are going to talk a little bit about an introduction of what is fractional order calculus. And then we are going to talk about a permanent magnet synchronizing motors. And then we are to talk about matrix converter for AC energy, electric energy. And then we are to talk about, especially about the fractional order controllers. And then in the part 5 of this chat, we are going to talk about the controlling the PNSM using matrix converter. And then finally, I'm going to talk about a few results and also some conclusions. Okay, the conversion of AC for industrial application is really important, because with that, we don't use transformers to convert the DC to AC and also AC. That's been that we want just use some electronic devices to convert directly AC to AC, no transformer needed. And then in this paper, because this chat comes from a paper that I defend last year, some design simulation are going to be presented. Now we were talking with some students to reproduce some of these simulation results, produce that in experimental ones. What is a permanent magnet synchronized motor? In this case, we have not two fields that need external energy. In this case, one of the fields is going to be produced by permanent magnet, and the other one is going to produce by external energy. This is really important, because with that, we reduce the consumption of the energy of this kind of machines. For these simulations, we use, I talk about in plural because this work is not just doing by myself, with students and another professor from this faculty and from the external institutions. These are some of the parameters for this kind of motor. You can see, I'm going to just to enunciate some of them. The stator phasor resistance is very small as usual, 0.0485 ohms. And the quantity of the poles are 4 pairs, okay? These are the equations for the motors. In this case, we are using the equations that are linear. In this case, we are just doing some work with this machine, but in the part on where the motor is linear, okay? Not when this is starting and not when this is near the saturation, just in the linear part. Okay, this is a form what is a AC matrix. For that, you can see in this part, It's not working. Okay, but in the top of the figure, you can see a pair of IGBTs and then another 3 more in 3 sections. That means that we are going to use this pair of IGBTs to conduce the energy for one direction or the another one. In this case, remember, we are going to use AC in the input, and we are going to produce AC in the output as well. In this case, we have 3 phases. That's why we need 3 blocks of these 3 pairs of IGBTs, in this case, 6 individual IGBTs. There are many ways to produce the output in the AC matrix. And then the way we can do that depend on the algorithm that we are going to use. There are some of them that are very popular. In this case, we are using the one that is inside the MATLAB. If I remember well, this is come from directly for the Venturini algorithm. They in the MATLAB change a little bit, but you can consider that exactly the same. If you want to check in the literature, you can check this algorithm. It's not really easy. Here with us is Luis. He developed his master degree using this kind of algorithm, and they are not easy, isn't it? They are easy or not? They are not easy. But anyway, in this case, we are doing just simulation. In the case of Luis, Luis Angel, he done a lot of simulation as well, but also he constructed the device, okay? In this case, the apparatus. But what happened with the output when you use this kind of matrix converter? The output is really bad, okay? If you want to use directly the 3 phases from the AC matrix, your devices that are going to not work well, or even they are not going to work. And then you need filters in the output. That is really important, and also they contribute a little bit to improve the output, the input filter. And then for the AC matrix, we need input filter and output filter. Okay, what is fractional order? Really, I didn't remember to start with that. I just check in internet some information about fractional calculus because it's not new. I just checked here, and Leibniz has a prophecy about that in 1695, a letter, Leibniz discussed the possibility of the derivative of order, a half order, acknowledging as a paradox, with potential for future usefulness. And then around 3,000 or more years after that letter, we are using fractional order calculus. It's not new, okay? You want to check this in the literature, the integer calculus, like the integral and derivative that we normally study in the high school, some of them in the university, integer all the time. But what happens when you say there is not integer? We can use fractional order calculus. And then you don't have an integral like this. This is an integral because S is in the Laplace symbol, and then here we have S to the minus lambda, and then that is considered an integral. But what happens when lambda is not integer? Could be fractional. And then you have here not an integer integral, and you can say we want a quarter of the integral, half of the integral, a third of the integral, depending on what you want to do. And then there is a lot of information about that. In this case, I am using this, come directly for a paper that, believe it or not, is for people from here in Puebla. For me, it was a very good surprise, because when I was reading the papers, looking for papers to introduce me or to introduce myself to this area, this was in around six years ago when I was studying this topic. And that was, for me, it was a big surprise. Okay, I knew who is this because he's working here in the Polytechnica of Puebla in near West Otzingo. And then I was reading this paper. And then in this paper, you can see here, using this transformation, this fractional integral can be reproduced by this, but also using this. And if you remember a little bit about your first courses of control, this is what? First is a filter, okay? We have here a zero, we have here a pole, and here we have a gain. And then using this, we can reproduce or emulate an integral, and fractional integral, really. The same thing, we can do this here with a derivative. With derivative, we can use exactly the same solution, but in this case, this is not to the minus, and then this is the Laplace, and then we have here a derivative. And using the same, we can reproduce this. But as you can see here, we can have a solution like this using an op-amp, operational amplifier. Okay, but also this filter, we can reproduce the filter using digital algorithms. That for us is better. Why it is better digital from you compare with analog? Because if you want to reproduce a big controller using fractional, you need a lot of amplifiers or pumps. But with the digital, with just one board, you can reproduce or use this algorithm. Okay, and then we change the solution, not using analog solution, but the digital solution. And then we translate from Laplace to see the function, and then we can use that. And also, we have here a zero, we have here a pole, and with this, we can say that we are emulating the fractional thing. Okay, again, if you remember your courses in control, we have the body graph. What is the effect of the pole in the magnitude when you compare input and output? Normally is a line like this that is descending with 20 decibel by decade, okay? But what happened in the phase, you are going to have a dephasing of 90 degrees. What if this is not an pole that is a total pole, okay? The fractional of a pole, or that is saying that is a fractional of an integral. And then you have a line like this with descending not 20, but maybe 10 or 5 or 15. But also the same with the phase. It's not going to be 90, it's going to be 80 something, 75, for example. Here is 50 or 30 or 20, okay? This is the degree they're going to be at the phase in minus, okay? It's going to be the same here with the zero, could be the same, okay? But the other way, okay? Well, but we have a little problem. We have really to think about this relationship, because this relationship is going to change the point where you are going to have the effect of the pole. What is that? I am talking about this line, this part. If you want the pole here, it's okay. But what happens you want your pole in this way or in that direction? Then you need to change the factor RG. In this case, we have the factor of 1, the factor of 0.1 or 0.01 when you multiply RG and CG. Remember, what is this? Allow me to return to to this one. Here, this is what I'm talking about. Okay, this relationship. These are really important. What is the value of this capacitor? What is the value of this resistor? And also the value of this capacitor, but it's connecting directly to CG with this A. Remember, the A is the gain of the filter. And then this is what I'm telling you. You are going to move this. And then how do you select that? Depending on your system. If your system is in the dominant pole is in some point, in some part of the graphic or in frequency, then this one needs to be around this. Okay, this why is that? What happens in a normal system when you have some poles that are really far away from the dominant pole? You can reproduce that, not exactly, but almost the same response without taking into account that kind of pole that are really far away. Really, this is the definition of dominant pole. A dominant pole, what is that? It's a pole that his value determines the way of our system is going to perform. What happens when the other poles? Okay, they are going to produce some kind of characteristic in your system, but not going to be dominant, okay? And then normally when you are working with a system with a lot of poles, sometimes you can say, okay, I'm going to take into account just these 3 or 4 poles. What happened with the other one? I'm not going to take into account with this model. Then you use your knowledge about the system. Maybe you are going to produce a good controller for that. And then if you want, you can change the system to the full one. And then we are going to know what happened with the system, with the full system, with your control. And then you are going to change your mind. Maybe that's going to be different, but normally there are not a lot of difference with a system with a few poles, with a system with a lot of poles. Okay, that's why we can say that. And then, what is the pole that we are going to take in account, or what are going the poles that we are going to take in account to fix the RGCG factor? The dominant ones. There is only one, it's okay. There are 2 or 3 of them. Then I'm going to put around this area or this value your RG factor, okay? Well, here we have PID, but it's not the normal PID that we are used to use. Here we have a fractional integral. We have a fractional derivative. And then instead of 3 parameters to tune or to set for the PID, we have 5, okay? Why 5? The gain, proportional gain, integral gain, derivative gain, but also fractional integral and fractional derivative. And then we have 5 of them. This is hard, could be hard sometimes. It's not easy to tune sometimes a PID, you know that. And sometimes we just use MATLAB and then use AutoTune, that's all. But now we have 5 of them. What you can do with this? There is a lot of solution for this. Really, this is an open area of research to know how to tune effectively fractional order. But if you read a little about classical control, it also, the PID, you cannot say this is the best, we say, method to tune a PID. No, there are not. Depend on your system all the time. If your system has some condition, some parameters that are not easy to solve, and you need to use another kind of method to tune your PID. And then you translate or transform this one, you can use this, okay? If you can see here, U is again here a 0, a pole, and the factor for the integral part. And for the derivative part, also again, a zero, a pole, and the normal gain for the derivative. And then we need to use this. Here we have one, Muñiz Montero, sorry, Muñiz in Spanish. Muñiz Montero is a professor in the Polytechnic of Puebla. He wrote this chapter for a book. For me, was really useful. Okay, this is the same equation, but now in formal pictorial form. And you can see here also this one. But you can see here, what we have here, a lead lag compensation, really. And then you have a fractional order controller, but if you read a little bit about that, that is really a problem of compensation. It's a compensation. But you have two of them, one for the integral part and other one for the derivative part. Before start with the machine, with the permanent magnet motor, allow me to use this for a very simple equation. In this one, we have a system with this gain, very big, but with two poles. A pole in 0, another pole is in -600, okay? And here we are using a very demanding computing time program, this one, and this one that is using a compensator, that is really very fast if you compare that with another solution. What we are doing here, we are comparing two ways to reproduce a PID fractional, okay, or fractional order PID, two ways. The first one is a computational demanding, and the other one is the one that is very fast, okay? And we have this result for this equation that is quite easy, no? The normal PID, you can see there, is the blue one, has an anti-wind up problem, a lot of integral. Okay, we tend to reduce that, but when we reduce that, that was very slow. And then, you know, normally when you are doing a control, you need to balance your solution. What do you want? Speed, reduce the problem with the step, or what do you want to do with your control? Okay, and then the other one, I can say the pink one, I don't know how, the fuchsia one in Spanish, is this one, okay? It's fast, it's really fast, but also has a little problem when it is returning to the set point. And that red one is the one that we want to reproduce here. It also has this. Then this one comes from the program. This one comes from the compensation one. Okay. And what happened with the effort of control? With the effort of control in the PID, as we don't have some saturation thing here, normally in a PID, in the part on the output in the control signal, we normally use a saturation block to to reproduce something that could be near to the real thing. What is that? What happens you are doing this in the real world? What happens if the PID say the control signal is 1000? First you say, what means 1000? 1000 what? Could be 1000 volts. Really? Really? From your control, you can go to the system 1000 volts? No, normally no. What is the normal one? Could be minus 15 to 15 or 12 or maybe 20, 24 as much, but not 1000. And then here, normally in this part, but in the PID, we use a saturation block, okay? And here you can see, this is the effort of control or the value of the control signal for the three controllers. And the one from the PID, a normal PID, is very large, is almost 30. Could be in this one 28 or 29, okay? As you can see here in this one, for the one that we are going to use, that is not really large. It's a little large because it's more than 15. If you want to use your normal power supply, you're not going to get more than 15, okay? Well, but also, we want to use some kind of adapted algorithm for this kind of control for these machines. But it could be not really good for us if we compare the gain scheduling for the PID, for the fractional order PID, but we use a fixed PID. It's not good to be good for our knowledge because if you use an adapted algorithm and you compare that with a classic algorithm, the adapted normally is going to be better. And then in this case, we are going to change the both controllers. The both controllers are going to be gain scheduling. What is gain scheduling? Gain scheduling, in this case, we select some parameters and we change the two parameters for the PIDs depending on the value of this signal, okay? In this case, the signal that we're going to use is what is the value of the amplitude of the, do you want to, in the output of your voltage, okay? You want a big one, you want a small one, a medium one, and depending of this, you're going to change the set of parameters for your PIDs. One of sets are going to be for the fractional, and the other one are going to be for the classical one, okay? And then here we have the control, could be fractional or could be classical PID. We have the process. We are checking the process, and depending on some of the value of the process, we are going to adjust the control parameters, and we are going to change that in our controller, okay? How do you select that? Depending on the process. How much you are going to change that? Depending on the process also, okay? You can change every volt, could be okay. You want to change every microvolt, depending on you, okay? Normally,
5 minutes left.
okay. Normally, we don't have a lot of change, okay? Depending on the process, really. But you can select some kind of index to check the performance, and then if the performance is okay, when you select the division for the change of parameters, is okay for the process. Okay, we select the two parameters for the system, and these are our results. Okay, first, we have here in the first graph the velocity or the speed of the motor compared with the reference, okay? You can see here, we have some oscillation here that is quite normal in this kind of solutions, okay? When we compare the PID where the fractional order PID, using, in this case, we are using the absolute error index, is better this one than the classical one. And here, I like this a lot because you can see here the input of the signal, the output from our converter, and the output using the, remember I told you about the filters. This is after the filter, this is before the filter. You can see there is a very good signal that is going to be inside the machine, okay? Well, what happens when you change, if you have some problems with your line? You have three phases, and what happens if one of the phases, it could be the phase A, reduce the value, and you have an unbalance in your three signals for the three-phase input, okay? here you are going to have something like this. It's going to reduce a little bit the amplitude, but you have no problem with the speed. You are going to maintain the speed. Doesn't matter that the amplitude of one of the phases has problem. How much can be reduced? 10%, 50%. More than that, you are going to check the problem. You are going to see the problem in the output. Okay, that means that these lines are going to be maybe in this part. Okay, also we have the voltage here, and what happened with the harmonics. Here are the harmonics with the ACIC with the filters, and here without the filters. This is with filters, and this one are without the filters. The filters are really important with this. Okay, this is also the same. Okay, well, allow me to draw some conclusion. The effectiveness of the gain scheduling fractional order PID driving ACIC matrix converter has been, checking in that is okay with simulation. Okay, the performance of the filters are really necessary to be really okay, because if not, the signal are going to be really, really bad, and then your machine is not going to work well. Okay, in the case of an imbalance or unbalance in the voltage, the fractional order is working really, really good. Okay, this is an open area of research, I just told you, and then we are really working on that. We are not working right now in the permanent magnet motors. We are working more in the converters. Okay, we are using this kind of controller for DC-DC converters. And we have now a DC quadratic converter that is working with classic PIDs. Is working now very well. We have some publication about that, comparing the PID with another kind of controllers, like some not really new, but not far away in the time. But we want to compare this classic PID control with a fractional one. Okay, one thing that is really good here, that even with an Arduino, you can reproduce the algorithm that you have in MATLAB. For a student, this is really good, but because you don't need a really powerful board or target to do that. Okay, with Arduino, with a very cheap, you can reproduce this kind of result, but not in MATLAB, in real world. Thank you very much.
Any question? Please. Only one.
In the part of the converters, which is the part of where you are focused, in speed or precision?
More in precision, because these are using for DC buses. And then when you have, you need really 5 volts. And then when you start your equipment, is going to move from the voltage in the input, and then it will present 5 volts in the output. Just it's going to move from maybe 12 to 5, just one. And then you need to maintain 5 volts. Doesn't matter how many loads you put in this line. Okay? And then we are working more for the precision, not in the velocity or the speed to go from one voltage to another one. Okay. Because this is the use that we're going to do with our development. Okay.
Thank you.
Anna?
How many decreasing harmonics in the signal with fractional order PID?
It's more than 30 or 40%. Yeah, but that is because the filter, not only because the controller,
Okay.
to be honest. Okay, if you want to use this controller without filter, you're going to have a lot of noise. Let me explain you a little bit about the DC-DC converter that we are working on now. We have in the output a lot of oscillation. With the fractional order, we reduce this a little bit. But if you compare that with a classical control, really is minimum. That's why, okay. Really the controller in this case helps to maintain the voltage in the values that we want, but not to reduce really that. For that, we are now applying a very fast commutation time. Okay, in this case, normally a converter works for 100 kilohertz, and now we are working near the 1 megahertz. And then with this change, really is 10 times, we are reducing this oscillation in the output. Okay, but if you want to use just the controller to reduce this kind of harmonics, it's not going to work. A little bit, but it's minimum really.
Another question? No? Okay, well, thank you, Dr. Herman.
Thank you.
Please, the forum. Well, with this, we end this day of a lot of talks. And we will meet you tomorrow for more talks. And now we will have a break, and later on, the presentation of the posters. Okay? Thank you very much.
Muy buenas tardes a todos. Agradecerles su asistencia a este evento. Nada más para